The tooth is no longer than a few centimeters. Its crown is worn smooth along one edge, and the stone around it is the dull brown of an English road cutting after rain. Nothing about it suggests a giant. There is no skull attached, no skeleton waiting beneath the surface, no footprint broad enough to hold a pool of water. There is only enamel, a root, and a pattern of ridges that looks strangely familiar. It resembles the tooth of an iguana, but it is far too large to belong to any iguana anyone has ever seen. In the early 19th century, that small contradiction was enough to open a new chapter in the history of life. Before Iguanodon had a body, it had a question. What kind of animal could leave a tooth like this in the ancient rocks of southern England? The answer would take more than half a century to assemble. It would pass through private collections, quarries, lecture halls, anatomical arguments, public spectacles, and a coal mine hundreds of meters beneath Belgium. Each new bone would change the animal. Each new reconstruction would reveal as much about the scientists who built it as about the dinosaur itself. Few prehistoric creatures have been imagined so many times or have so completely recorded the changing way humans learned to see dinosaurs. Iguanodon was not the first extinct reptile recognized from fossils, and it was not the first dinosaur to receive a scientific name. Megalosaurus had been formally described in 1824. But Iguanodon did something different. Its teeth showed that enormous prehistoric reptiles were not all predators. Some were herbivores, built to crop and process plants. That fact helped transform a handful of disconnected bones into the beginnings of a whole terrestrial world. It also made Iguanodon one of the three animals Richard Owen later used when he established the group Dinosauria in 1842. The dinosaur that changed science did not do so in a single moment. There was no clean revelation in which one fossil supplied every answer. Instead, Iguanodon changed science by repeatedly forcing it to correct itself. First, it was known as a tooth. Then, as a gigantic lizard. Then, as a heavy, horn-nosed quadruped. Then as an upright, kangaroo-like biped with a spike on each thumb. Later, it became a more horizontal animal, capable of carrying weight on its hands. Today, even that familiar image is still being tested as researchers revisit its locomotion, growth, diet, relationships, and the circumstances of its death. If these journeys through the dinosaur age are what bring you to Jurassical, subscribing keeps the next one close. To understand why a tooth could matter so much, we have to return to a time before the word dinosaur existed. In the 1820s, geology was changing quickly, but the history of life was still being assembled from fragments. Fossils were known. Extinction was increasingly accepted. Georges Cuvier had demonstrated through comparative anatomy that bones from the past could belong to animals with no living equivalent. Marine reptiles such as ichthyosaurs and plesiosaurs were emerging from the cliffs of southern England. Yet the idea that immense, land-dwelling reptiles had once formed a major part of terrestrial ecosystems was only beginning to take shape. The rocks of Sussex were especially important. Across the Weald, layers of sandstone, clay, and silt preserved the remains of early Cretaceous rivers, floodplains, ponds, and forests. These deposits were not understood in the modern way, with precise radiometric ages and a global geological timescale. But they were clearly ancient, and they contained bones, scales, shells, plants, and teeth that did not fit comfortably into the living world. Quarries and road cuttings exposed these layers as people dug for stone and improved routes between towns. Industrial work was opening windows into deep time without intending to. The traditional account places Mary Ann Mantell at the center of the first discovery. According to the story, she found unusual teeth in 1822 while accompanying her husband, Gideon Mantell, on a visit to a patient near Cuckfield. Other historical accounts suggest that quarry workers or local collectors may have supplied some of the earliest specimens. The exact path by which every tooth reached Mantell is not completely secure. What is clear is that Marianne and Gideon Mantell are closely associated with the first known material, and that Gideon recognized the teeth as evidence of an animal unlike any then described. Gideon Mantell was a physician. His medical practice demanded long days and travel through the Sussex countryside, but geology occupied nearly every space around that work. He collected fossils, corresponded with other naturalists, published descriptions, and built a collection that eventually filled rooms. For him, the Wealden rocks were not simply layers beneath fields and roads. They were the remains of an ancient environment. Every shell or bone could help reconstruct that environment, but the strange teeth presented a particular difficulty. They looked herbivorous, they also looked reptilian, and they were much larger than the teeth of any living plant-eating reptile. Imagine the calculation hidden inside that observation. A modern iguana has a body that can be held in human arms, if tooth size scaled directly with body size. The fossil animal might have been enormous beyond reason. Early estimates became exaggerated because the relationship was treated too simply, but the basic conclusion was right. The tooth had belonged to a very large herbivorous reptile. That combination was new. The great fossil reptiles then attracting attention were often interpreted through the anatomy of crocodiles, monitor lizards, or marine predators. Here was evidence for a giant that ate plants. The name Iguanodon means, in essence, iguana tooth. Mantell compared the fossil to the serrated teeth of a living iguana and used that resemblance as the foundation for the name. It was a practical act of comparative anatomy. The fossil did not match the iguana in every detail, and the animal was not simply an enlarged iguana, but the comparison provided a biological clue. The crown had a broad, leaf-like shape. Its margins carried denticles. Wear showed that opposing teeth had met and worked against one another. Even before the rest of the skeleton was understood, the mouth was already suggesting an herbivore capable of processing resistant vegetation. Mantell did not immediately receive universal agreement. When isolated fossils are all that exist, identity can shift with every comparison. Some authorities initially considered the teeth to be mammalian or fish-like. Cuvier himself, after seeing drawings or specimens, at first offered interpretations that did not recognize the animal Mantell imagined. Later he reconsidered. This was not unusual failure. Comparative anatomy depends on available examples, and there was no complete skeleton against which the tooth could be checked. The category itself was missing. Scientists were trying to identify a dinosaur before anyone had defined dinosaurs. In 1825, Mantell published his formal notice on the newly discovered fossil reptile from the sandstone of Tilgate Forest. The paper did not present an animal as we know it now. It presented a set of arguments. The teeth resembled those of an iguana. Their size implied a very large body. Associated bones suggested a reptile of extraordinary dimensions. The deposits appeared to have formed in a freshwater or terrestrial setting rather than in the open sea. Taken together, the evidence pointed toward a gigantic herbivorous reptile that had lived on land in a remote geological age. That publication gave the tooth a name, but not yet a face. For years, Iguanodon existed as an outline around missing bones. Its scale could be guessed. Its diet could be inferred. Its habitat could be approached through the sediments and plant fossils around it. Almost everything else remained open. There was room for a sprawling lizard, a rhinoceros-like reptile, or something no living animal could properly represent. The uncertainty was not a weakness at the edge of the story. It was the story. Modern paleontology often presents a dinosaur through a finished skeletal diagram, every known bone placed in relation to the next. Early Iguanodon research worked in the opposite direction. A tooth was compared with a living reptile. A limb fragment was compared with a large mammal. A vertebra was tested against crocodiles and lizards. Separate finds from different places and perhaps different animals could be grouped together because no better framework existed. The researchers were building both the creature and the rules by which creatures like it would be studied. This is one reason Iguanodon became so influential. Its fossils were discovered during the formation of vertebrate paleontology as a discipline. Questions that now seem ordinary had to be asked for the first time. How much could a single tooth reveal about diet? Could limb proportions reconstruct posture? How should bones from different quarries be assigned to one species? What happens when a new skeleton contradicts a famous model? Iguanodon would become a test case for all of them. The consequences reached beyond the animal. A giant herbivore required abundant vegetation. Abundant vegetation implied productive landscapes. A large terrestrial reptile required muscles, circulation, digestion, reproduction, and movement on a scale that the old image of sluggish, marginal reptiles did not easily explain. Once Iguanodon was accepted, the ancient world could no longer be filled only with monsters wading in swamps or predators roaming empty ground. It needed forests, floodplains, plant communities, prey, competitors, and time enough for whole ecosystems to develop and disappear. All of that began inside a worn crown of enamel. The first Iguanodon was small enough to rest in a hand, but it carried evidence for an animal that would eventually stand in museums above crowds. Between the tooth and the mounted skeleton lies one of the longest corrections in the history of paleontology. To follow it, we have to stay with the fragments and watch the body grow around them. The Iguanodon deposits that produced the earliest Iguanodon fossils were formed during the early Cretaceous, more than 120 million years ago. Southern England was not then an island set beneath cool Atlantic weather. It lay farther south, within a warmer world where sea levels, rainfall, and coastlines changed across long intervals. Rivers moved through broad lowlands. Channels shifted, flooded, and abandoned their courses. Mud settled in ponds and overbank areas. Sand accumulated where currents were stronger. Leaves, wood, shells, bones, and footprints entered those sediments in different ways, preserving only selected pieces of the living landscape. Mantell was interested in more than naming animals. He wanted to reconstruct the country in which they had lived. Plant remains from the same rocks suggested conifers, cycads, ferns, horsetails, and other vegetation. Freshwater shells and fish pointed toward inland waters. Crocodilian fossils and turtles added further detail. The picture was incomplete, but it was recognizably terrestrial. Iguanodon was not a sea monster washed into a marine deposit. It belonged to river plains and wooded ground, an animal moving through the same environments that produced fossil trunks and beds of clay. This distinction mattered because the fossil record familiar to many early geologists was strongly marine. Shells were abundant and easy to preserve. Marine reptiles had articulated skeletons in fine sediments. Land animals were more difficult. Their bodies were often scavenged, weathered, transported, and separated before burial. A tooth might survive where a skull did not. A limb bone might travel downstream without the rest of the body. Iguanodon entered science through exactly this uneven record. It was reconstructed from durable pieces that had been scattered by both ancient processes and modern collecting. The early name also carried a taxonomic problem that would last for generations. The original teeth were distinctive enough to establish a general kind of animal, but not detailed enough to define every later skeleton with confidence. During the 19th and 20th centuries, many large ornithopod fossils from Europe, North America, Asia, and elsewhere were assigned to Iguanodon because they looked broadly similar. The genus became a container for animals that shared a body plan rather than a precise identity. Much later, researchers would separate many of those fossils into other genera. The confusion began with the understandable limitations of the first material. In the 1820s and 1830s, however, the immediate task was simpler: find more of the animal. Mantell gathered vertebrae, limb bones, jaw fragments, and other remains from the Iguanodon. Some were clearly part of a large herbivorous reptile. Others were difficult to distinguish from the remains of different dinosaurs that were not yet recognized. Even where the assignment was correct, the bones did not arrive as a connected skeleton. Their relationships had to be inferred. A femur showed size and weight-bearing. A tooth showed feeding. A vertebra showed the construction of the spine. None showed how the whole animal stood. Living analogs offered help, but also imposed limits. If the teeth resembled those of an iguana, it was natural to imagine an iguana-like body enlarged to extraordinary size. If the limb bones were massive, a rhinoceros could provide a sense of support and bulk. Comparative anatomy works by finding shared structure, yet extinct animals can combine features that do not coexist in living species. Iguanodon had a reptilian skull, a beak, complex toothwear, powerful hindlimbs, weight-bearing hands, and a specialized thumb spike. No modern animal supplied a complete template. One of the most important early discoveries came from a quarry near Maidstone in Kent in 1834. Workers blasting stone exposed a large slab containing numerous bones. The specimen was damaged during excavation, and it was not a complete articulated skeleton in the modern sense, but it brought together more of Iguanodon than had previously been available in one place. Vertebrae, ribs, limb elements, and parts of the pelvis lay within the rock. For Mantell, the slab offered a chance to move beyond isolated fragments and imagine the animal as an integrated body. The Maidstone specimen also illustrates how fossils can become cultural objects before their scientific meaning is settled. The slab was displayed, studied, drawn, and discussed. Its bones were difficult to interpret because they overlapped and remained partly embedded. Preparation methods were limited. Some pieces could be mistaken for others, and the orientation of the skeleton was not obvious. Yet the specimen carried authority simply because so much of the animal appeared to be present. It seemed closer to a final answer, even when many of the crucial connections were still uncertain. From such material, Mantell revised his ideas about Iguanodon. He recognized that the hindlimbs were large and powerful, while the forelimbs appeared comparatively smaller. This opened the possibility that the animal was not a simple four-footed lizard. He also interpreted a conical bone as a horn and placed it on the nose. That decision became one of the most famous errors in dinosaur reconstruction. The bone was real. The error lay in its position. Decades later, complete hands from Belgium would show that the supposed nasal horn was the first digit of the hand, transformed into a spike. It is easy to treat the misplaced spike as a joke made by primitive science, but the mistake was reasonable within the evidence available. The isolated element had no obvious counterpart among familiar animals. A horn was plausible for a large herbivore, especially when rhinoceroses influenced the imagined body. The hand itself was unknown. Without the neighboring wrist and fingers, there was no direct anatomical route back to the correct position. The error survived because no specimen had yet preserved the necessary context. Fossils do not label themselves. A bone can carry precise information about muscle attachment, growth, stress, and relationship, but only after its identity and orientation are understood. Turned around or moved to the wrong part of the body, it can support an entirely different animal. Iguanodon would repeatedly demonstrate this dependence on context. The same spike could produce a horned quadruped or a hand armed with a rigid thumb. The object did not change. The reconstruction around it did. By the late 1830s, Mantell had become one of the best-known popularizers of geology in Britain. His books brought fossils and deep time to readers far beyond specialist societies. Iguanodon became central to that work because it made the vanished world tangible. A shell could show that a sea had once covered the land. A giant reptile suggested something more immediate, an animal with weight, appetite, movement, and a place in a landscape. It allowed geology to become a history of living worlds, rather than only a sequence of rocks. Mantell's personal life, however, became increasingly difficult. His medical practice, finances, health, and relationships suffered. He sold much of his fossil collection to the British Museum in 1838. A carriage accident in 1841 left him with a severe spinal injury and chronic pain. His rivalry with Richard Owen deepened as Owen's institutional influence grew. These circumstances should not be reduced to a simple morality play of a forgotten discoverer and a powerful rival, but the imbalance mattered. Scientific credit in Victorian Britain depended not only on evidence, but on access, reputation, class, institutions, and control over collections. Richard Owen was one of the leading comparative anatomists of his age. He had exceptional knowledge of vertebrate structure and a talent for drawing broad conclusions from fragmentary material. He also understood the importance of classification. By comparing Megalosaurus, Iguanodon, and Hylaeosaurus, Owen argued that these animals shared features separating them from ordinary lizards. In 1842, he placed them within a new group, Dinosauria. The word is often translated as terrible lizards, though Owen's intention was closer to fearfully great reptiles than to monsters in the modern sense. Iguanodon was essential to the definition. Megalosaurus represented a large carnivorous form. Hylaeosaurus contributed an armored body. Iguanodon supplied the giant herbivore. Together, they suggested a radiation of terrestrial reptiles with different diets and defenses. Owen emphasized their upright limb structure and sacral anatomy, features that distinguished them from sprawling living reptiles. His dinosaurs were not merely giant lizards. They were a particular anatomical group, and their bodies implied a terrestrial capability that older reconstructions had underestimated. The creation of Dinosauria did not instantly produce the modern evolutionary concept of dinosaurs. Owen worked before Darwin published On the Origin of Species, and his interpretations were shaped by different ideas about design, extinction, and the organization of life. The first dinosaurs were sometimes used in arguments that have little in common with present evolutionary biology, yet classification created a durable framework. Once Iguanodon, Megalosaurus, and Hylaeosaurus were recognized as related, every new discovery could be compared against a growing group rather than treated as an isolated curiosity. That change altered the meaning of future fossils. A new limb bone might belong not simply to an unknown reptile, but to a dinosaur. A pelvis could be examined for features shared across the group. Teeth could indicate different ecological roles within dinosaur communities. The name gave researchers a question to ask: what makes a dinosaur a dinosaur? Iguanodon helped make that question possible, even though the animal used to answer it was still incorrectly assembled. Credit and conflict followed. Owen's public authority often overshadowed Montel's earlier work, and the two men disagreed over anatomy and interpretation. Montel continued revising Iguanodon, at times moving closer to a more lightly built and potentially bipedal animal. Owen favored a more massive quadruped. Their arguments were scientific, personal, and institutional at once. The animal became a field on which competing visions of prehistoric life were displayed. Neither man would see Iguanodon in anything close to its modern form. Montel died in 1852. Owen lived long enough to witness later discoveries, but the complete Belgian skeletons would expose major errors in the model he helped place before the public. The first age of Iguanodon had been built from teeth, slabs, and comparisons. The next would be built at full scale. For the first time, dinosaurs were about to leave papers and cabinets and become bodies large enough for people to walk around. Iguanodon would stand in a park, solid and horned, as an image of the ancient world. It would be wrong in ways that now seem obvious. It would also change how science reached the public. In South London, beside the relocated Crystal Palace, an artificial landscape took shape during the early 1850s. Islands rose from lakes. Geological layers were arranged as visible scenery. Full-sized models of extinct animals appeared among reconstructed plants and rocks. The project was intended to educate, entertain, and display Britain's confidence in science and industry. At its center stood Iguanodon, not as a skeleton, but as an entire animal rendered in brick, iron, cement, and paint. Sculptor Benjamin Waterhouse Hawkins built the prehistoric animals under Richard Owen's scientific direction. Hawkins had to solve a problem no one had attempted on this scale: There were no complete dinosaur skeletons, no wildlife photographs, and no tested method for translating scattered fossil bones into a life-sized exterior. The models therefore combined anatomy with engineering and artistic judgment. Their internal structures had to support enormous masses of material. Their surfaces had to suggest skin and muscle. Every uncertainty had to be given a physical shape, because a sculpture cannot remain partly hypothetical. The Crystal Palace Iguanodon was a heavy quadruped. Its body was low and barrel-shaped. The limbs were thick and columnar. The head carried the conical spike on its nose. Its proportions drew from large mammals and living reptiles, producing something that looked like a rhinoceros crossed with a giant lizard. This was not careless fantasy. It reflected the dominant interpretation available to Owen and Hawkins. The sculpture made the evidence visible, but it also made the gaps visible to later generations. A drawing can be revised with a line. A paragraph can be qualified. A multi-ton sculpture in a public park gives uncertainty a permanence it does not deserve. Once completed, the Crystal Palace dinosaurs became more than scientific proposals. They became landmarks. Visitors encountered them as objects with weight and authority. Children saw Iguanodon before they understood how little of the original animal had been known. The reconstruction entered public memory, where images often survive longer than the arguments that produced them. Before the park opened, one of the models hosted a famous dinner on New Year's Eve in 1853. Guests sat at a table arranged inside the unfinished mold of an Iguanodon. Scientists, engineers, artists, and officials ate beneath a painted canopy while banners celebrated the ancient creatures around them. The event was theatrical, but its symbolism was precise. Human beings were dining inside an animal that had disappeared more than 100 million years earlier. An animal reconstructed through the new authority of geology. The dinner has sometimes been described as occurring inside the finished dinosaur itself, but it took place within the mold used during construction. That distinction matters because the event has accumulated legend in the same way the animal accumulated anatomy. What survives in popular culture is a compressed image, Victorian gentlemen eating inside an Iguanodon. The reality was slightly different, but no less remarkable. Paleontology had become spectacle before it had become secure. Crowds arrived after the park opened in 1854. They saw extinct life integrated into a landscape rather than isolated in a case. The models suggested scale in a way bones rarely could. A tooth might be impressive because of what it implied. A full-sized Iguanodon confronted visitors with the implied body directly. It stood beside water and vegetation, occupying space like a living animal. The ancient world had been turned into a place that could be entered. This changed science communication. The Crystal Palace sculptures were among the first major attempts to present prehistoric animals to a mass public as reconstructed organisms. They linked research, art, engineering, and commercial leisure. They also established a pattern that continues in museums, films, books, and digital models. Paleontology rarely communicates through bones alone. It creates bodies around them. Those bodies are necessary, powerful, and temporary. It would be easy to measure the Crystal Palace Iguanodon only by its errors. The nose horn was wrong. The posture was wrong. The body was too mammalian and too lizard-like at the same time. The hands and feet lacked the specializations later skeletons would reveal. Yet the model got something important right. Dinosaurs were terrestrial animals with substantial bodies, not merely enlarged versions of fragile modern reptiles. It treated Iguanodon as a serious component of an ancient ecosystem, worthy of reconstruction at monumental scale. Public images also influence scientific expectations. Once a model becomes famous, new fossils are often interpreted against it. Bones that fit are welcomed. Bones that do not fit must overcome the authority of the established form. Iguanodon would experience this repeatedly. The animal became a visual tradition before its skeleton was known. and each later reconstruction had to dismantle a previous one in the public mind as well as in anatomy. During the decades after Crystal Palace, additional fossils continued to emerge from Britain and continental Europe. Some suggested more gracile proportions. Others were assigned to Iguanodon because few alternative names existed. Trackways indicated three-toed dinosaurs moving across soft sediment, but connecting a track to a particular skeleton remained uncertain. The growing collection increased knowledge while also increasing confusion. More bones did not automatically produce a clearer animal when they came from different species, ages, and environments. The 19th century genus Iguanodon expanded far beyond the fossils that had defined it. Large ornithopod remains with broadly similar teeth and limbs were frequently placed under the name. Species accumulated. Some were based on limited material, some later proved to belong elsewhere. This practice was common in early paleontology because the comparative collections were small and the range of dinosaur diversity was underestimated. A familiar genus became the default destination for unfamiliar bones. The result was an animal with unstable boundaries. Iguanodon could be described as though it were one widespread, long-lived form. Yet, the fossils assigned to it might represent multiple lineages separated by millions of years and large distances. The name became scientifically useful and scientifically dangerous at once. It allowed communication, but it concealed diversity. The eventual sorting of that material would become another way Iguanodon changed science, demonstrating that famous genera are not protected from taxonomic revision. Meanwhile, the physical fossils presented their own problems. Bones collected from the Wealden could be crushed, incomplete, or distorted by pressure. A skeleton is not preserved as a neutral anatomical diagram. Sediment compacts. Minerals replace tissue. Joints separate. Scavengers move pieces. Water sorts them. Quarry tools break them. Preparation removes surrounding rock but can also remove evidence. Every reconstruction begins after a long chain of alteration. Scientists learn to read those alterations more carefully. A flattened bone might need to be mentally restored to its original shape. A missing surface could be reconstructed from the opposite side. Associated bones could be distinguished from articulated bones. The position of a fossil in sediment could reveal whether a carcass decayed in place or was transported. These methods developed across many discoveries, but Iguanodon repeatedly supplied the material on which they were tested. Still, the central problem remained. No British specimen had yet provided a row of vertebrae connected from neck to tail, a pelvis linked to both hindlimbs, and hands preserved with their strange digits in place. The Crystal Palace animal was an answer built before that evidence existed. Somewhere else, beneath a landscape not yet associated with dinosaurs, the missing context had already been buried. The place was Bernissart, a mining village in Belgium. There, industrial workers descended through carboniferous rocks in search of coal. Their tunnels entered a geological structure filled with much younger clay. The miners were not looking for Cretaceous animals. The museum in Brussels was not expecting a dinosaur graveyard. The encounter began as an obstruction in a mine. In the spring of 1878, at a depth of roughly 322 meters, miners working in the Saint-Barbe pit broke into a pocket of clay. Within it were dark, mineralized objects. Some appeared to be tree trunks. Pyrite glittered across them like gold. The material was worthless to mining, but the shapes were unusual enough to attract attention. When fragments were brought upward and recognized as bone, the scale of the discovery began to emerge. A telegram reached the Royal Museum of Natural History in Brussels on April 12, 1878. What followed would become one of the most extraordinary excavations in the history of dinosaur science. The mine had not exposed one isolated skeleton. It had entered a deposit containing many large articulated animals. For the first time, Iguanodon would be recovered not as a set of possibilities, but as body after body preserved in the ground. The Crystal Palace reconstruction had given Iguanodon a public shape. Bernissart was about to take that shape apart. Recovering a dinosaur from an open quarry is difficult. Recovering dozens of them from a working coal mine more than 300 meters underground required an entirely different kind of operation. The fossil-bearing clay lay within a natural pit cutting through much older coal measures. Galleries were narrow, wet, and dependent on supports, pumps, ventilation, and constant attention to the stability of the surrounding rock. Every bone had to be documented, protected, divided into manageable sections, and moved through the mine before it could ever reach daylight. The museum sent specialists to Bernissart, and excavation began under the direction of Louis de Pauw, the institution's chief preparator. Geological advice and scientific oversight involved figures including Alphonse Briart and Pierre-Joseph van Beneden. Miners supplied the underground knowledge and labor without which the work would have been impossible. Paleontology at Bernissart was not a solitary scientist brushing sand from a bone. It was a coordinated industrial project conducted inside an active and hazardous mine. The skeletons lay largely articulated. Vertebrae remained in sequence. Limbs were associated with bodies. Hands preserved their individual digits. Skulls could be connected to necks. This did not mean the animals were untouched. Many bones were flattened, cracked, or chemically unstable. Some skeletons overlapped. But the arrangement retained something earlier Iguanodon fossils had lacked: anatomical relationships. The ground itself showed which bone belonged beside which. Workers exposed the fossils gradually, strengthening them as they appeared. Sections were recorded and lifted in blocks. Plaster, glue, paper, and supporting materials helped hold the clay and bone together during transport. Each package had to travel through underground galleries, rise in the mine cage, and continue to Brussels. The process lasted for years. Between 1878 and 1881, the deposit yielded a collection unmatched by any previous dinosaur discovery. Official accounts often describe around 30 relatively complete Iguanodon skeletons. Broader assessments of the material count the remains of approximately 37 or 38 individuals, depending on how fragmentary specimens are included. The distinction reflects different ways of counting, not a disagreement over the significance of the site. Bernissart preserved many large ornithopods, several of them close enough to complete that their bodies could be reconstructed with a confidence impossible from the English teeth and scattered bones. Picture one of those skeletons before excavation. The skull rests in clay. The spine curves away through darkness. Ribs collapse around the space once occupied by lungs and digestive organs. The pelvis lies heavy beneath the body. A hand is folded near the chest, and on that hand the first digit ends in the conical bone that had spent decades on the nose of a sculpture in London. No announcement is needed. The correction is present in the anatomy. The hands were among the most revealing parts of the discovery. Iguanodon did not have 5 similar fingers arranged like those of a large lizard. Each digit was specialized. The thumb formed a rigid spike. The middle 3 fingers were bound into a strong weight-bearing unit with blunt, hoof-like terminal bones. The 5th finger was more mobile and projected outward, potentially useful in handling vegetation. One hand contained defense, support, and manipulation within the same basic structure. The exact functions of the thumb spike remain open to interpretation. It could have served in defense against predators, in contests between individuals, or in other close-range interactions. The bony core would have been covered by keratin, making it longer and sharper in life. Biomechanical work supports the idea that it could resist substantial forces, but fossils cannot preserve the behavior itself. The spike is best treated as a capable structure, rather than assigned to a single certain use. The forelimbs also changed the animal's posture. They were not as short as a kangaroo's arms, nor arranged like the sprawling limbs of a lizard. The wrists and central digits could transmit weight. The shoulders were robust. The palms faced inward rather than downward, a point often missed in older mounts and illustrations. When the animal placed its hands on the ground, it supported itself along the central fingers without twisting the forearm into an anatomically impossible position. The hind limbs remained longer and more powerful. This combination produced a body unlike either of the two old extremes. Iguanodon was not the low quadruped of Crystal Palace, but neither was it simply a giant reptilian kangaroo. Its locomotion involved a more complicated balance between forelimbs, hindlimbs, body mass, age, and speed. The Bernissart skeletons provided the data, but interpreting that data would still take generations. The skulls confirmed a beaked herbivore. The front of the jaws lacked teeth and would have carried a keratinous covering for cropping plants. Farther back, batteries of replacement teeth formed working surfaces. Iguanodon did not possess the densely packed dental batteries of later hadrosaurs, but its jaws were more effective at oral processing than those of many earlier dinosaur herbivores, where facets showed repeated contact. The mouth was not merely clipping vegetation and sending it untouched into the gut. For scientists accustomed to building Iguanodon from isolated teeth, the Bernissart skulls created an unusual reversal. The part that had first defined the animal could now be placed inside a complete feeding system. Tooth shape could be related to jaw motion, beak width, muscle attachment, and skull flexibility. The original comparison with an iguana remained visible in the name, but the complete animal made clear how far the dinosaur had moved beyond that initial analog. The fossils carried a hidden threat. Many bones were permeated by pyrite, an iron sulfide mineral formed during burial. Underground, within stable clay and low oxygen, the pyrite could persist. Once excavated and exposed to air and changing humidity, it could oxidize. The reaction produced acids and expanding minerals that split bone from within. A specimen that had survived more than 100 million years could begin to crumble after entering a museum. Conservators treated the bones with the methods available at the time. Preparators removed unstable material, soaked or coated specimens, filled cracks, and supported them with armatures. Some techniques helped. Others later created complications as glues aged, metals corroded, or coatings obscured surfaces. Conservation is itself a historical process. A museum fossil does not stop changing when excavation ends. It continues to react with air, temperature, humidity, supports, and every substance used to preserve it. This chemical instability shaped the scientific life of the Bernissart collection. The skeletons became national treasures and research specimens, but their fragility limited how often they could be dismantled, remounted, sampled, or moved. The famous upright mounts preserved a 19th century interpretation, partly because changing them would risk the original bones. The display became a record of both dinosaur anatomy and conservation history. Preparation in Brussels required years. Each block had to be opened. Bones were cleaned and hardened. Corresponding sections were fitted together. Missing parts were modeled where necessary. The scale of the collection demanded systematic labeling and storage. The work converted an underground accumulation into scientific specimens, but it also removed the bones from their sedimentary context. Detailed plans and notes therefore became essential evidence for later attempts to understand how the animals died. The mine closed the distance between deep time and industrial time. Coal workers entered rocks formed in Carboniferous swamps, then crossed into a younger Cretaceous deposit holding dinosaur skeletons. One excavation existed because another had cut through it. The energy source powering 19th century industry led directly to animals that would transform 19th century science. By the early 1880s, the museum possessed something no institution had ever held before: multiple nearly complete skeletons of a large dinosaur from the same locality. One complete animal can show anatomy. Many can show variation. Differences in size, proportions, scars, and bone form can reveal growth and individuality. Bernissart made Iguanodon not just reconstructible, but comparable with itself. That abundance also created new questions. Were the smaller skeletons juveniles, females, or a different species? Did all the animals die together? Were they members of a herd? Did they live near the site or arrive from elsewhere? Did the deposit represent one catastrophe or repeated deaths? Some answers proposed in the 19th century would later be rejected. Others remain uncertain today. Exceptional preservation does not eliminate ambiguity. It changes its scale. The person most closely associated with interpreting the new skeletons was Louis Dallo, a young engineer who turned toward paleontology. He studied the Bernissart material in detail and helped create the reconstruction that replaced the Crystal Palace animal. His Iguanodon stood upright, balanced on powerful hind limbs and a trailing tail. The horn moved from the nose to the hand. The dinosaur had changed again. For the first time, the public would see Iguanodon built from a nearly complete skeleton. The correction was enormous. It was also incomplete. Louis Dallo approached the Bernissart skeletons with an advantage no earlier researcher had possessed. He could compare complete animals, examine repeated structures, and test whether an unusual bone appeared in the same position from one individual to another. Anatomy that had once depended on isolated pieces became anatomy supported by pattern. The spike belonged to the thumb because the hands preserved it there. The pelvis, spine, and limbs could be connected because several skeletons repeated the same arrangement. Dallo also recognized that Iguanodon was capable of a more elevated posture than the Crystal Palace model suggested. The long hind limbs, robust pelvis, and relatively shorter forelimbs seemed to indicate bipedal movement. At the time, large living kangaroos offered a persuasive analog, an animal standing upright on powerful legs, using a heavy tail as a third support, and holding the forelimbs away from the ground. The comparison produced a new Iguanodon that appeared athletic and distinctly dinosaurian. One of the Bernissart skeletons was mounted in 1882. Building the display required suspending bones from an adjustable framework so their relationships could be tested before final support was added. The resulting animal stood tall, its torso raised steeply, its tail descending to the floor, its forelimbs lifted, and its head carried above visitors. This was one of the earliest mounted dinosaur skeletons available to the public, and among the first, based on such complete material. The effect must have been extraordinary. Crystal Palace had shown a body imagined around fragments. Brussels displayed the actual bones of a single giant animal, arranged into a form more than twice the height of a person. The skeleton did not ask visitors to trust a sculpted surface. Vertebrae, ribs, pelvis, limbs, and skull were visible. The evidence itself had become monumental. Dallo's reconstruction corrected major errors. The nose horn disappeared. The specialized hand became visible. The hind limbs were recognized as longer than the forelimbs. The animal no longer sprawled close to the ground. These were substantial advances, and the upright Iguanodon dominated scientific and popular imagery for decades. It appeared in books, murals, toys, and museum displays. Once again, a reconstruction moved from current hypothesis into visual certainty. The problem lay in the tail and spine. The Bernissart skeletons preserved long tendons that had ossified along the back and tail, stiffening the vertebral column. To make the animal stand in a strongly upright tripod, the tail had to curve sharply downward. That bend was not compatible with the natural structure. In life, the tail extended more directly behind the body as a counterbalance. The famous mount achieved its pose by forcing a rigid system into a shape it could not comfortably hold. A skeleton can be complete and still be misunderstood. The bones reduce uncertainty, but they do not arrange themselves into motion. Joints have ranges. Ligaments limit those ranges. Muscles pull across them. Cartilage creates spaces that dry bone does not show. Gravity acts on the entire body. Dallo had far more evidence than Owen, yet he still worked through living analogs and assumptions that shaped the final result. Early 20th century researchers generally retained the upright bipedal model. Dinosaur tracks were sometimes interpreted as evidence of large animals walking on 2 feet. The tail-dragging tripod seemed stable for display. It also fit a broader image of dinosaurs as unusual but somewhat awkward reptiles. capable of standing yet dependent on the tail as a prop. Iguanodon became one of the standard examples of this posture, along with other large ornithopods. Museum mounts reinforced the idea because they were difficult to change. Steel supports were built for a specific pose, fragile bones were attached to them. Galleries were designed around the resulting height. Publications copied the mount. Artists copied the publications. Each copy removed the original uncertainty a little more. After enough repetition, the posture appeared to be an observation rather than an interpretation. The upright animal also affected how its behavior was imagined. If the forelimbs were held permanently off the ground, the hands could be treated mainly as weapons or grasping organs. If the body stood vertical, feeding height increased. If the tail rested on the ground, trackways might be expected to show drag marks. These connected assumptions formed a coherent picture, which made the picture harder to dismantle. Changing posture would require changing ecology, movement, and the function of the hand at the same time. By the later 20th century, dinosaur biomechanics and trackway analysis were moving toward more horizontal reconstructions. Researchers re-examined the articulations of vertebrae, the distribution of ossified tendons, and the structure of the forelimb. In Iguanodon, these features supported a trunk held closer to horizontal, with the tail projecting behind rather than dragging. The animal's center of mass shifted forward compared with the old tripod. Its hands were no longer decorative additions. They could contact the ground. The middle three fingers formed a compact column. Their terminal bones were broad rather than claw-like. The wrist was relatively restricted. The forearm could not rotate the palm flat against the ground in the human manner. Instead, the hands faced inward, and weight passed through the central digits. This anatomy makes sense in an animal that sometimes, or perhaps often, moved quadrupedally. It makes much less sense in one that kept the hands permanently elevated. For many years, the standard modern interpretation described Iguanodon as a facultative biped, an animal able to move on four limbs during ordinary walking or feeding and rise onto two for faster movement or access to higher vegetation. Growth may have affected that balance, with smaller individuals proportioned differently from large adults. Recent biomechanical reassessments have argued that mature Iguanodon may have been more committed to quadrupedal locomotion than previously assumed, perhaps even obligately so under ordinary conditions. The debate is active because posture is reconstructed from anatomy, trackways, and mechanical modeling rather than direct observation. Whatever position ultimately proves most accurate, the old kangaroo pose is not supported. The back was not steeply upright. The tail did not serve as a permanent third leg. The animal's body extended forward and back around the hips, balanced more like the bodies of other dinosaurs. When the forelimbs reached the ground, they did so through specialized weight-bearing hands. Iguanodon had become a dinosaur without needing a living mammal to supply its entire silhouette. This change is often presented as a sequence of increasingly correct pictures: lizard, rhinoceros, kangaroo, horizontal ornithopod. The sequence is useful, but it can hide the real process. Each reconstruction answered questions that mattered at the time. The first tooth established diet. The Crystal Palace model communicated scale. Bernissart established the skeleton. Modern biomechanics rebuilt movement. New work now tests the modern consensus. Science did not move because earlier researchers were foolish. It moved because evidence accumulated and methods improved. Iguanodon therefore became one of the clearest public demonstrations that scientific images are provisional. The animal in a museum is never a recovered photograph of the past. It is an argument assembled from bone. The argument can be strong, but it remains open to revision. Iguanodon has been revised so visibly that its changing poses now form a history of paleontology in themselves. Even the mounted Bernissart skeletons carry multiple times at once. Their bones formed in the early Cretaceous. Their burial reflects a local environment and a later geological collapse. Their excavation belongs to 19th century industry. Their posture records Victorian anatomy. their conservation records generations of chemical treatment. Their present interpretation draws on digital models and comparative datasets that Dallo could not have imagined. One specimen is a layered archive of animal, rock, museum, and idea. The museum in Brussels eventually displayed the Bernissart iguanodons within a vast glass enclosure. Visitors could look across several upright skeletons standing together, an arrangement that magnified the sense of a herd. The scene became one of the most famous dinosaur displays in Europe. Because the original fossils are fragile, the historic mounts remain substantially in the positions created for them. Nearby reconstructions and casts can show more modern postures without forcing the old bones through another dangerous transformation. This separation between original and updated reconstruction is valuable. It preserves the history of interpretation instead of erasing it. A corrected mount might present a better iguanodon, but it could destroy evidence of how the Bernissart fossils entered science. Museums increasingly treat historic displays as artifacts in their own right, especially when they have shaped public understanding for more than a century. Beneath the posture debate lies a more intimate question. What was this animal actually doing with its body on an ordinary day? A skeleton can tell us where muscles attached and which joints bore weight. It cannot directly show a herd crossing a floodplain, an adult lowering its head to feed, or a thumb spike driven toward a predator. To approach the living iguanodon, we have to move from the museum frame into the anatomy itself. A mature Iguanodon bernissartensis was a large animal, commonly reconstructed at roughly 9 to 10 meters in length, with mass estimates in the range of several metric tons. Exact numbers vary because fossils differ in size and because body mass must be modeled from skeletal dimensions. It was not among the largest dinosaurs, but it was larger than any living terrestrial herbivore except the biggest elephants. Its body combined deep abdominal volume, powerful hindquarters, a long balancing tail, and a relatively small head at the end of a muscular neck. The torso had to contain an extensive digestive system. Plant matter is difficult to break down, especially when the available vegetation includes fibrous conifer foliage, ferns, and other resistant tissues. Large herbivores often rely on microbial fermentation, allowing bacteria and other microorganisms to process cellulose within expanded regions of the gut. Soft organs do not fossilize in ordinary iguanodon skeletons, but the broad ribcage and herbivorous dentition support an animal built to consume and digest large amounts of vegetation. The pelvis anchored powerful muscles for the hindlimbs and tail. The femur was thick and long. The lower leg and foot carried the body over 3 main toes, each ending in a broad hoof like ungul rather than a sharp predatory claw. These feet distributed force across soft ground. Trackways made by large iguanodontian dinosaurs show 3-toed impressions with rounded digits, sometimes accompanied by smaller handprints when the animal moved on all fours. Trackways are appealing because they seem to capture behavior directly. A skeleton records a dead body. A trackway records an action: a foot lowered, weight transferred, toes pushed away. Yet footprints are also shaped by mud depth, water content, the collapse of sediment beneath the surface, and erosion after the track was made. A broad print can belong to a narrow foot sinking deeply. A missing handprint does not always prove bipedal movement, because forefeet may have touched lightly or landed on firmer ground. The evidence is immediate and complicated at once. No trackway can be assigned to Iguanodon bernissartensis with absolute certainty unless it occurs alongside diagnostic skeletal remains, which is rare. Paleontologists instead compare track shape, size, age, and regional dinosaur faunas. Large 3-toed tracks from early Cretaceous Europe are often described as iguanodontian. They show that animals with this general body plan moved across floodplains and shorelines, sometimes alone and sometimes along parallel routes. They support locomotor interpretations without identifying every track maker to genus. The tail was not a passive extension. Muscles at its base helped control the hindlimbs and stabilize the body. Farther back, Ossified tendons limited excessive bending and kept the tail firm. In a horizontal posture, the tail balanced the weight of the chest, neck, and head. During turns, it contributed rotational inertia. During movement, it shifted subtly with the body rather than dragging as dead weight. The structure that made the Victorian tripod impossible also made efficient dinosaurian balance possible. Along the back, the vertebral column carried repeated stresses from walking, feeding, and supporting the gut. Ossified tendons formed a lattice that reinforced the spine. These rods are often visible on mounted skeletons as bundles crossing the neural spines. They did not turn the body into an inflexible beam, but they reduced unwanted motion. A large herbivore benefits from stability. Every sway of several tons must be corrected by muscle, and wasted motion becomes expensive over thousands of steps. The neck was shorter than that of a sauropod, but long enough to expand the feeding envelope around the body. Without moving its feet, Iguanodon could lower the beak toward ground vegetation, sweep across shrubs, and raise the head into lower branches. Older reconstructions sometimes gave it a giraffe-like tongue for gathering food, but the supporting bones of the tongue indicate a robust muscular organ better suited to manipulating food within the mouth than reaching far outside it. The skull appears modest beside the body, but it contains much of what made Iguanodon successful. The snout broadened toward a toothless beak. Cheek regions held rows of tightly arranged teeth. Openings reduced skull mass while leaving strong arches for muscles. The jaw joint and tooth rows created a feeding apparatus capable of repeated oral processing. This was not mammalian chewing in every mechanical detail, but it moved beyond the simple vertical bite of many reptiles. Iguanodon replaced its teeth continuously. As a functional tooth wore down, another developed beneath or behind it. The process maintained an active cutting and grinding surface despite constant contact with abrasive plants and sediment. Unlike humans, which receive only 2 generations of teeth, many reptiles and dinosaurs renewed teeth throughout life. For a multi-ton herbivore, this was essential. A worn-out mouth would be fatal long before the rest of the skeleton failed. Earlier interpretations proposed that the upper jaws could flex outward slightly as the mouth closed, creating a transverse grinding action. The precise mechanics of ornithopod feeding remain debated and varied among groups. What is secure is that Iguanodon teeth developed broad wear facets through contact with opposing teeth, and that the jaws processed food more thoroughly than the peg-like cropping systems of sauropods. Its descendants and relatives would later carry this trend to extremes in the dental batteries of hadrosaurs. A single Iguanodon tooth therefore connects the first discovery to the animal's everyday life. Mantell saw an enlarged resemblance to an iguana and inferred herbivory. Modern analysis sees enamel thickness, denticles, wear direction, replacement pattern, and microscopic traces of contact. The same object holds more information because the questions have multiplied. Behind the mouth, jaw muscles attach to the skull and lower jaw, generating force through repeated bites. The beak cropped stems and leaves. The cheek teeth broke material into smaller pieces. The tongue moved the food. Swallowing delivered it to a large fermenting gut. Energy extracted from that vegetation powered growth, reproduction, body heat, and movement. Iguanodon's scientific importance can make it seem like an idea first and an animal second, but every famous bone belonged to a body that spent most of its life finding and processing food. The hand remains its most distinctive structure. Digit 1 became the thumb spike, held away from the central weight-bearing fingers. Digits 2, 3, and 4 formed the supportive core. Digit 5 was smaller, flexible, and opposable only in a limited sense, able to move outward and perhaps hook or draw branches toward the beak. The whole hand was neither a hoof nor a grasping paw. It was a set of specialized tools sharing one wrist. Popular images often show iguanodons stabbing attackers with both thumbs like paired daggers. The anatomy allows the spike to function as a weapon, but the actual motion would have been constrained by shoulder, elbow, and wrist joints. It was probably most effective at close range, driven by the forelimb, or used to resist contact. It may also have played a role in display or competition. Fossils rarely preserve direct evidence of soft tissue injuries inflicted by thumb spikes, so confident scenes of combat go beyond what the record can currently demonstrate. Predators nevertheless shared Iguanodon's world. Large theropods lived in early Cretaceous Europe, including forms related to Allosauroids and Spinosaurids. A healthy adult Iguanodon possessed size, powerful limbs, a heavy tail, and thumb spikes. Juveniles would have been more vulnerable. Sick, injured, or isolated adults could also be attacked. Defense was not one weapon, but a combination of awareness, movement, body mass, social context, and anatomy. The old question of whether Iguanodon traveled in herds is harder than museum displays suggest. Bernissart contains many individuals, and some track sites preserve multiple Iguanodontian paths. Both are consistent with group behavior, but neither proves a permanent herd. Animals can gather seasonally, concentrate near water, follow the same route at different times, or die in repeated events. Modern herbivores use a wide range of social systems. Iguanodon may have done the same. Growth added another dimension. Juveniles were not simply miniature adults. Limb proportions changed as the animal gained mass. Muscle attachment surfaces strengthened. The balance between two-legged and four-legged movement may have shifted. Bone tissues recorded periods of faster and slower growth. By comparing multiple Bernissart individuals and other specimens, researchers can examine variation that would be invisible in a species known from one skeleton. Every adult began inside an egg, though eggs and nests confidently attributable to Iguanodon remain rare or uncertain. The absence is a reminder that even famous dinosaurs can have major parts of their biology missing. We know the hand in extraordinary detail, but not the appearance of a nest. We can model jaw movement, but not hear a call. The fossil record is generous in one place and silent in another. To fill those silences responsibly, paleontologists compare close relatives, living birds and crocodilians, trackways, bone histology, and the environments preserved around fossils. Inference is necessary. The line between inference and evidence simply has to remain visible. Iguanodon has spent 2 centuries teaching that lesson. Its most famous wrong reconstructions began when a plausible inference hardened into a fact before enough anatomy existed to test it. Leave the museum and place the animal back into the early Cretaceous. The ground is low and wet, but not everywhere swamp. River channels cut through broad plains. Sand builds into bars. Fine mud spreads during floods and settles in shallow basins. Patches of woodland rise on better drained ground. Ferns occupy disturbed margins. Conifers form stands along the horizon. The landscape changes from season to season and from one river bend to the next, creating a mosaic rather than a single endless forest. Iguanodon bernissartensis lived during the Barremian and into the early Aptian part of the early Cretaceous, roughly around 126 to 122 million years ago, though exact ages vary by locality and geological correlation. Its fossils are best known from Western Europe, especially Belgium and parts of Britain and the Iberian Peninsula. At that time, Europe consisted of islands, coastal lowlands, shallow seas, and intermittently connected land areas. Geography shifted as sea levels rose and fell. The climate was generally warmer than today, without permanent polar ice sheets on the modern scale. Warmth did not mean uniform tropical rainforest. Rainfall varied. Some environments experienced pronounced wet and dry seasons. Rivers flooded, then contracted. Vegetation responded to local soils and water. Pollen and spores recovered from Iguanodon bearing deposits show conifers, ferns, and other non-flowering plants, with early flowering plants beginning to appear in the broader early Cretaceous world, but not yet dominating most landscapes. A 2024 study of the Morella Formation in northeastern Spain examined fossil pollen and spores associated with Iguanodon bernisartensis, and compared several Western European localities. The results indicate that the species occupied a range of environments rather than one narrow habitat. Conifers and ferns were likely important food resources. This does not provide a menu for a particular individual, but it connects the animal's jaws to the plant communities preserved in the same sediments. A fern frond is not dramatic beside a skeleton. Yet it is closer to the daily life of Iguanodon than most imagined battles. Thousands of bites would pass through vegetation like this. Young shoots, leaves, twigs, and low branches supplied the energy that built femurs, replaced teeth, and drove migrations or local movements. The animal's world was made not only from predators and catastrophes, but from repeated feeding at the edge of water. An adult could browse across several vertical levels. On 4 limbs, the beak reached low plants and shrubs. Raising the front of the body, whether briefly or regularly, could extend access into higher foliage, though the degree of bipedal feeding depends on the locomotor interpretation adopted. The long neck increased reach without requiring the animal to move its entire mass for every mouthful. A few steps opened another wide arc of vegetation. Large herbivores reshape the environments they feed in. Modern elephants break branches, strip bark, open paths, and alter the density of woodland. Iguanodon was not an elephant, and direct comparison has limits, but an animal of several tons consuming large quantities of plants would have affected vegetation. Groups or repeated visits could maintain open areas, damage young trees, and transport seeds or spores indirectly through disturbed soil and dung. The dinosaur was part of the physical process of the floodplain. Fossil evidence does not yet allow precise estimates of daily food intake. Metabolic rates in non-avian dinosaurs are reconstructed from growth, bone tissue, body size, and comparisons with living animals, and different methods yield different values. Iguanodon was likely more physiologically active than the sluggish reptiles imagined by many Victorians, but describing it with a single modern metabolic category may oversimplify. It was a dinosaur with its own combination of growth and energy use. Seasonal change would matter even in a warm climate. Plant quality declines as leaves mature. Water sources shrink or expand. Floods can isolate patches of ground. Reproduction may be timed to periods of greater food availability. Isotopic studies of Bernissart teeth and bones published in 2025 suggest that at least those animals were not long-distance migrants and occupied a relatively restricted region with marked seasonality. The chemical signal is a new line of evidence, but it should not be treated as a complete map of movement for the entire species. Isotopes enter an animal through water and food. Oxygen can reflect climate and drinking water. Strontium relates partly to local geology. As teeth and bone tissues form, those chemical signatures become incorporated into mineral. Millions of years later, careful sampling can compare values through growth layers or across individuals. The result is not a photograph of a root. It is a pattern that can support or weaken hypotheses about where the animal lived. The same method must account for fossilization. Groundwater can alter original chemistry. Pyrite formation, mineral replacement, and later conservation treatments complicate interpretation. Researchers therefore analyze trace elements and preservation history alongside biological signals. Bernissart's fossils are unusually complete, but chemical completeness is a separate question. Every result depends on distinguishing what came from the living animal from what entered after burial. The floodplain carried risk. Heavy rain could raise rivers quickly. Saturated banks collapsed. Mud trapped feet. Drought concentrated animals around shrinking pools. Carcasses drew crocodilians, fish, insects, and theropods. A large body could survive many ordinary hazards, yet size also made escape from unstable ground more difficult. The same sedimentary systems that supported vegetation could become the mechanisms that buried bone. Predatory dinosaurs in Western Europe included several large theropod lineages. though not every predator lived at the same time and place as every Iguanodon population. Spinosaurids occupied river-rich environments and fed at least partly on aquatic prey, while large allosauride relatives and other theropods were capable of attacking terrestrial dinosaurs. Smaller predators targeted juveniles, eggs, or injured animals. The ecosystem distributed danger across body sizes. Bite marks on Iguanodon bones are not abundant enough to reconstruct a single standard predator-prey relationship. In many fossil ecosystems, evidence of feeding appears as punctures, scores, broken teeth, or healed injuries. The absence of marks can result from preservation and sampling. It does not mean predation was unimportant. It means the specific scenes remain mostly unrecorded. A living Iguanodon would have spent much of its time detecting what the fossil record rarely preserves. Smell carried information from water, vegetation, other animals, and decay. Footfalls traveled through soil. Calls or low-frequency sounds may have coordinated spacing. Vision identified movement along forest edges. The skull allows some study of sensory anatomy through the shape of brain cases and inner ears, but the social meaning of those senses remains inferential. The eyes were positioned laterally enough to provide broad awareness rather than the strongly forward-facing field of a dedicated predator. The head did not need to strike with jaws. It needed to find vegetation, monitor surroundings, and coordinate with the body during feeding and movement. The inner ear helped stabilize gaze as the animal walked. Balance was an active neurological process, especially when several tons shifted between 2 or 4 limbs. Smaller animals filled the spaces around it. Turtles occupied ponds and channels. Crocodilians waded near water. Fish moved through rivers. Lizards and early mammals lived beneath vegetation and in burrows. Pterosaurs crossed overhead. Insects fed on plants, wood, dung, and carcasses. Many of these animals are represented at Bernissart and other Wealden localities by bones, teeth, scales, shells, or impressions. Iguanodon was the largest visible presence, but it was not alone. The soundscape would be unfamiliar without being silent. Wind moved through conifer branches, water struck exposed roots. Insects produced rhythms unlike a modern summer because flowering plant pollinators had not yet transformed terrestrial communities. Dinosaurs called, stepped, and fed. A beak cut through stems. A heavy foot compressed mud, leaving a 3-toed track that filled slowly with water. Those tracks sometimes preserve changes in direction and speed. Parallel trackways can suggest animals moving through the same area, though whether together or at separate times depends on sedimentary detail. Handprints may show quadrupedal progression. Toe orientation can reveal how the foot met the ground. Track depth can estimate pressure only cautiously. The surface records an event, but the event must be reconstructed from deformation in mud. The landscape also explains why Iguanodon became known so early in Britain. Wealden rocks were exposed where people quarried stone and where coastal erosion cut cliffs. Fossils became accessible because ancient rivers deposited them, and modern geology later lifted and revealed those deposits. Discovery is never determined only by where animals lived. It also depends on where rocks survive, where humans dig, and which specimens are recognized. Iguanodon likely ranged through more than one habitat across Western Europe. The species appears in deposits representing river plains, vegetated lowlands, and areas influenced by nearby coasts. Its robust body and versatile feeding system may have allowed it to exploit varied plant communities. That ecological flexibility would help explain why a dinosaur known first from isolated English teeth could later appear in large numbers in Belgium and in substantial remains farther south. Yet the most famous population did not leave its history across a broad plain. It accumulated inside a deep geological structure at Bernissart. To understand why so many skeletons remain together, we have to look below the animals, into the basin, the collapsing rock, and the clay that sealed them away. Across the wider Wealden world, Iguanodon shared the land with herbivores built on very different plans. Armored dinosaurs carried plates, spikes, and heavy skin bones close to the ground. Smaller ornithopods moved on long hind limbs and fed beneath the height reached by the giant Iguanodontian. Sauropods persisted in some early Cretaceous European communities, extending their necks into vegetation beyond Iguanodon's usual range. Several herbivore strategies could occupy the same broad landscape because they divided food by height, plant type, habitat, and season. Competition would still occur. A drought could narrow the available green vegetation along water. Flooding could remove feeding ground and redistribute plant communities. Large animals might displace smaller ones from favored patches, while smaller species could exploit dense cover or low-quality vegetation inaccessible to a heavy body. Fossils identify the participants more readily than the daily negotiations between them. Ecology must be reconstructed from body size, teeth, abundance, and environment. Iguanodon's broad beak suggests it gathered vegetation in substantial mouthfuls rather than selecting individual leaves with great precision. The mobile fifth finger may have helped pull branches, though the range and importance of that behavior remain uncertain. Its feeding envelope overlapped with both low and intermediate vegetation. By moving between open fern-rich ground and wooded margins, it could change diet as local conditions changed. Plant fossils do not always represent what grew exactly where a dinosaur fed. Pollen travels on wind, rivers carry leaves and wood, spores concentrate in water. A deposit can mix vegetation from uplands, banks, and local wetlands. Diet reconstructions therefore compare several sites and several kinds of evidence. A conifer-dominated pollen assemblage does not prove that every meal was conifer foliage, but it establishes what was available within the regional environment. Fire may also have shaped some early Cretaceous landscapes. Charcoal occurs in many Mesozoic deposits, showing that vegetation burned where oxygen and dry fuel allowed it. After a fire, ferns and other opportunistic plants can spread rapidly across open ground. Large herbivores may be attracted to fresh growth. The cycle of burning, regrowth, browsing, and sedimentation could create patches of habitat that changed over years rather than geological ages. At Iguanodon scale, the landscape would be experienced differently. A channel narrow to a map could be a barrier to a juvenile and a few steps for an adult. Dense young conifers could hide smaller animals but only reach the chest of a mature individual. A seasonal flood covering kilometers of plain might redirect movement for weeks. Body size turns geography into biology. European geography added another layer. Shallow seas divided land into islands and peninsulas whose connections changed with sea level. Populations could become isolated, then reconnect. Isolation encourages anatomical divergence over generations. This shifting geography helps explain the variety of iguanodontians found across Western Europe and why fossils once grouped under Iguanodon are now separated into different genera. An animal does not experience continental drift or evolutionary isolation as concepts. It encounters coastlines, river mouths, storms, and the absence or presence of roots. A population restricted to one region may gradually differ from relatives elsewhere. Millions of years later, taxonomists identify those differences in bones. The branching tree of iguanodontians was built from ordinary limits on movement. Seasonal storms could move saltwater into lowlands or send freshwater far across coastal flats. Plant communities shifted with salinity and drainage. Track surfaces formed, dried, and vanished. Carcasses entered channels. Bones were buried in one basin and destroyed in another. The patchiness of the fossil record reflects this environmental patchiness. Iguanodon bernisartensis appears to have tolerated more than one local setting, but tolerance is not the same as indifference. Access to fresh water, suitable vegetation, stable breeding areas, and roots across the landscape would still limit distribution. The isotopic evidence for restricted movement at Bernissart suggests that these animals did not need to cross enormous distances to survive. A productive regional mosaic may have supplied what they required throughout the year. That conclusion applies most directly to the sampled individuals. Other populations, climates, or age groups may have moved differently. Large herbivore behavior can vary within one species. Some modern populations migrate while others remain resident. Fossil chemistry gives a local answer, and local answers accumulate into a species-level picture only after multiple sites are compared. A broken fern stem, a polished tooth, and a narrow band of isotope values all point toward the same quiet fact. Iguanodon belonged to a place. It was not a generic dinosaur walking through interchangeable scenery. Its anatomy met the plants, water, ground, and seasons of early Cretaceous Western Europe. When those conditions changed, the animal moved, adapted, or disappeared. Bernissart was not an ordinary floodplain burial. The dinosaur-bearing clay filled a natural pit formed within older rocks. Deep below the Cretaceous surface, soluble material had been removed, and the overlying ground subsided, creating a steep-sided depression. Water and sediment collected inside it. Over time, the basin received plant debris, aquatic animals, terrestrial carcasses, and repeated flows from unstable margins. The structure acted as both habitat and trap, though exactly how the iguanodons entered remains debated. Early explanations often imagined a single herd overwhelmed by catastrophe. The completeness of the skeletons and their concentration made a mass death seem obvious. Perhaps the animals fell into a ravine, drowned in a flooded basin, or sank into mud. Such scenarios remain possible in general form, but later, geological work indicates a more complex history. The fossil layers may represent repeated depositional events within a deepening sinkhole lake rather than one sudden disaster. Taphonomy is the study of what happens between death and discovery. It examines body position, articulation, breakage, scavenging, sediment, chemistry, and the sequence of burial. At Bernissart, many skeletons are complete or nearly complete and remain articulated. That suggests limited transport after decomposition began. Yet the animals occur at different levels and orientations, and the surrounding sediments record changing conditions. The evidence must explain both preservation and repetition. A carcass entering deep, low-oxygen water can avoid some scavenging. Soft tissues decay. Gases may make the body float temporarily. Limbs and skull can shift as ligaments weaken. Eventually, the remains settle. Fine sediment covers them. If burial is rapid enough, much of the skeleton stays together. If water remains calm and bottom conditions exclude large scavengers, even delicate bones can survive close to their original positions. The Bernissart deposit also contains fish, turtles, crocodilians, plant remains, and other fossils. These organisms help reconstruct the basin as a freshwater environment connected to the surrounding landscape. The small crocodilian Bernissartia takes its name from the locality. Its presence, along with aquatic fossils, shows that the pit was not simply a dry hole into which dinosaurs fell. It held water and supported a community. One possibility is that iguanodons died near or within the basin during separate episodes. Carcasses may have been carried short distances by floods or debris flows. Slope failures from the sinkhole margins could have introduced sediment and bodies. Periods of deeper water may have favored preservation. No single mechanism has yet explained every skeleton, and the site cannot be reopened casually because the original mine workings are inaccessible and hazardous. Modern projects have therefore treated Bernissart almost like a cold case. Researchers revisit 19th century maps, excavation drawings, specimen labels, sediment samples, borehole data, and the skeletons themselves. Digital models can restore the positions of fossils within the pit. Geochemistry can identify water conditions and later alteration. Sedimentology reconstructs the movement of material into the basin. The investigation depends on evidence collected across more than a century. A line in an old excavation plan can become as important as a bone. Once a skeleton is removed, its original relation to the surrounding layer is lost unless someone recorded it. The depth, orientation, and neighboring fossils may determine whether animals died together or at different times. Burnous art shows why field notes are part of the specimen. Without them, the fossil keeps anatomy, but loses part of its history. The apparent dominance of adults also affects interpretation. If a social herd died in one event, age distribution might reflect the herd's structure. If the basin accumulated carcasses repeatedly, adult bias could result from body size, habitat preference, transport, or preservation. Smaller juveniles may have lived elsewhere, escaped particular hazards, decomposed more completely, or remain undercounted because their bones were harder to recognize. The sample is large for dinosaurs and still selective. Death assemblages can imitate behavior. A group of bodies resembles a group of animals, but the connection is not automatic. Modern watering holes can collect individuals that arrived days or months apart. River channels concentrate bones from wide areas. Droughts produce mixed accumulations. Sinkholes can trap animals repeatedly. Paleontologists therefore separate evidence for association in life from association after death. Burnous art may still preserve social information, but it does not provide a simple photograph of a herd. The safest conclusion is that many iguanodons occupied the regional ecosystem and that unusual geological conditions concentrated and preserved their remains. Whether they moved as stable groups, seasonal aggregations, or more loosely connected individuals must be tested with other evidence. Fossilization began as tissues broke down in clay-rich sediment. Microbial activity altered the local chemistry. Iron and sulfur combined to form pyrite within pores and cavities. Mineral-rich water moved through the bones. Original organic material disappeared or changed. The skeletons retained external anatomy while their internal composition became a product of the burial environment. This replacement is why a fossil can be both bone and rock. Some original mineral may remain. Other parts are recrystallized or filled with new minerals. Microscopic structure can survive even when chemistry changes. Under thin section, growth lines and vascular canals may remain visible. Under a mass spectrometer, later elements can complicate the signal. Different methods see different layers of the same transformation. The pyrite that helped fill and preserve the bones later threatened them. Oxygen and moisture reached the fossils after excavation. Iron sulfide oxidized, producing sulfate compounds and sulfuric acid. Crystals expanded through cracks. Surfaces flaked. The decay could spread invisibly beneath consolidants. Conservators sometimes found that treatment which stabilized a specimen for decades had not stopped the underlying reaction. Modern conservation controls humidity, monitors chemistry, and uses imaging to locate internal damage. Digital scanning preserves geometry even if the physical specimen changes. Removable supports and reversible adhesives are preferred where possible. Yet no intervention is completely neutral. Sampling removes material. Coatings alter surfaces. Climate control requires continuous maintenance. Preserving burnous art is an active scientific commitment, not a one-time repair. The collection's survival is remarkable. The animals lived in the early Cretaceous. Their bodies entered a sinkhole basin. Minerals replaced tissues. Coal mining cut into the deposit. Workers recovered enormous blocks under dangerous conditions. Preparators spent years exposing the bones. Conservators fought chemical decay. Researchers continue to scan and analyze them. Each stage could have erased the evidence. Instead, the skeletons remain. This long survival changes how we define discovery. The miners found the fossils in 1878, but every generation discovers something different within them. Dallo found the hand and upright body. Later researchers found the horizontal spine and weight-bearing forelimb. Histologists find growth. Geochemists find water and movement. Engineers test the thumb spike. Taxonomists compare variation. The object remains the same while the accessible questions expand. Multiple burnous art individuals also help distinguish normal variation from species differences. One thumb spike may be larger than another. Vertebrae can carry different grooves. Limb bones vary in robustness. Some differences reflect age, sex, injury, or individual development, rather than separate taxa. Without a population sample, paleontologists may name a new species from a feature that falls within ordinary variation. Bernissart provides a rare baseline for avoiding that mistake. Even here, the baseline has limits. The sample comes from one region and a restricted interval of time. It may represent related animals or a local population. Variation elsewhere could be greater. Sexual differences are difficult to identify without preserved reproductive anatomy. Growth stages can overlap in size. Statistics help, but fossil samples remain smaller and more biased than samples available for living species. The skeletons under glass in Brussels are therefore not simply a herd stopped in motion. They are a geological accumulation, a conservation challenge, a population sample, and a history of reconstruction. Their stillness contains many processes. Water moved, clay slid, tissues decayed, minerals grew, mines opened, steel frames rose, scientific ideas shifted around them. Bernissart gave Iguanodon a body, but it also created a new problem of identity. Once complete skeletons existed, which earlier fossils truly belonged to the same genus? The name had already spread across continents and species. Bringing the animal into focus would require removing much of what had been placed inside it. Scientific names are intended to create stability, but they can also preserve the accidents of discovery. Iguanodon was named from teeth at a time when no complete skeleton existed and when the diversity of large herbivorous dinosaurs was unknown. As new fossils appeared, similarity to the familiar animal encouraged assignment to the same genus. The result was a taxonomic range far broader than the real biological range of any single species. During the 19th and much of the 20th century, species of Iguanodon were named from Britain, Belgium, Germany, Spain, North America, Mongolia, and other regions. Some were based on skulls or skeletons, others rested on teeth, vertebrae, or isolated limb bones. The genus became what paleontologists informally call a wastebasket taxon, a convenient category for material that resembled a known form but had not been compared within a sufficiently detailed evolutionary framework. Wastebasket taxa often arise early in the study of a group. The first named animal becomes the reference point. Later discoveries are pulled toward it because differences are treated as variation, preservation, or age. Only after enough specimens accumulate do researchers see repeated anatomical patterns that justify separation. What once looked like one widespread genus becomes a collection of related but distinct lineages. Iguanodon was especially vulnerable because the original English material was fragmentary. The historical species Iguanodon anglicus was based mainly on teeth that captured the broad feeding anatomy of an iguanodontian, but did not preserve enough unique features for easy comparison with complete skeletons. The much more complete Belgian species, Iguanodon bernissartensis, became the practical standard for the genus. In 2000, the International Commission on Zoological Nomenclature formally designated I. bernissartensis as the type species, stabilizing the name around the bernissart animal. A type species does not mean the first individual ever found, or the most common animal in a deposit. It is the nominal anchor for a genus. Other species belong in Iguanodon only if they are sufficiently close to that anchor under current taxonomic judgment. This decision allowed researchers to ask a clearer question: does a fossil truly share the defining anatomy of I. bernissartensis, or is it an iguanodontian that deserves another name? Several familiar animals moved out. The more lightly built Iguanodon atherfieldensis, known from excellent British material including a nearly complete skeleton, was reassigned to Mantellosaurus. Other species became Dacotodon, Beryllium, Hypsilospinus, and additional genera. Some names remain debated, and revisions continue as new analyses change relationships. The old Iguanodon did not shrink because fossils disappeared. It shrank because dinosaur diversity became clearer. This taxonomic narrowing can feel like loss. A famous genus once appeared across much of the world, then retreated toward a more limited set of bones and places. Scientifically, the opposite happened. Removing unrelated material restored information. Different body plans, geographic histories, and evolutionary experiments emerged from what had been a single blurred category. Names affect every later conclusion. If several species are incorrectly combined, estimates of body size variation become inflated. Geographic range appears wider. The genus seems to survive longer. Differences in skull shape may be misread as age or sex. Ecological flexibility can be exaggerated. Taxonomy is therefore not a clerical exercise performed after the biology is understood. It determines which fossils are allowed to answer biological questions together. The Bernissart collection again became crucial. Because many individuals preserved the same general anatomy, researchers could measure variation within eye. Bernissartensis, features once used to separate species could be tested across a population. Some differences proved inconsistent or overlapped between individuals. Others remained stable enough to support distinction. The mine yielded not only a reconstruction of one dinosaur, but a reference for defining its boundaries. Recent phylogenetic work continues to refine those boundaries. Analyses published in 2026 treat Iguanodon in the strict sense as the lineage of eye. Bernissartensis and place some Iberian forms previously assigned to the genus elsewhere within Iguanodontidae. Such results may change with new specimens and character datasets. The important point is not that taxonomy has reached a final answer. It is that the name now carries a much more precise burden of proof than it did a century ago. Phylogenetic analysis compares anatomical characters across many species and searches for evolutionary trees that best explain their distribution. Researchers code features of the skull, teeth, vertebrae, limbs, pelvis, and other structures. Computer algorithms evaluate alternative relationships. The output depends on which specimens are included, how characters are defined, how missing data are treated, and which analytical assumptions are used. A tree is a tested hypothesis, not a recovered family photograph. Within that framework, Iguanodon belongs to Ornithopoda, a major group of mostly herbivorous ornithischian dinosaurs. More specifically, it lies among advanced iguanodontians close to the evolutionary radiation that later produced hadrosaurids, the duck-billed dinosaurs. It was not necessarily the direct ancestor of those later forms. Evolution branches, but its anatomy preserves an intermediate combination: powerful hindlimbs, weight-bearing hands, a beak, complex toothwear, and a body plan approaching the highly successful hadrosaur condition. This is another reason the animal mattered. It stood near the center of a large evolutionary transformation in herbivorous dinosaurs. Earlier ornithopods were generally smaller and more lightly built. Later hadrosaurs developed extraordinarily dense dental batteries, expanded beaks, and specialized skulls. Iguanodon occupied a stage in which large body size, versatile locomotion, and increasingly effective oral processing were already established. Historical importance and evolutionary position can be confused. Iguanodon did not change science because evolution selected it for a special role. It changed science because its fossils were found at decisive times and in exceptional forms. Another dinosaur could have supplied similar evidence if its teeth had appeared in Sussex and its skeletons in Bernissart. The importance lies in the meeting between biological history and human history. The animal never knew it was representative. It did not stand between primitive and advanced forms in its own world. It fed, grew, reproduced, avoided danger, and died as a complete organism adapted to present conditions. Categories such as basal, derived, transitional, and iconic belong to our reconstruction. They are useful only if they do not reduce the animal to a rung on a ladder. Taxonomic revision also changes museum labels and public memory slowly. A skeleton displayed for decades as Iguanodon may now be Mantellosaurus. Older books remain in circulation. Toys preserve outdated names. Search results mix current and obsolete classifications. The public can interpret these changes as scientists being unable to decide. In reality, revision often signals greater resolution. The broad outline was replaced by a finer map. The same process occurs with anatomy. One study may emphasize facultative bipedality, another stronger quadrupedal commitment. One model may estimate 3 tons, another closer to 4. These are not arbitrary fluctuations. Different specimens, body reconstructions, and mechanical assumptions produce ranges. Good science makes those assumptions visible and tests them against new evidence. Iguanodon is unusually effective at revealing this process because its older images remain easy to compare. The Crystal Palace body, the Brussels tripod, the late 20th century horizontal biped, and modern quadrupedal reconstructions form a visual sequence. Taxonomy has a less visible sequence, but it is equally dramatic. A genus once spread across the globe has been cut back to an anatomical core. Some historical corrections also involve credit. Marianne Mantel's role in the first discovery has often been simplified, minimized, or romanticized. Quarry workers and local collectors who found fossils can disappear behind the name of the scientist who published them. Bernissart's miners are remembered unevenly compared with museum officials. Taxonomy records the names of authors, but discovery is usually collective and shaped by labor outside formal science. Reconstructing that history requires the same caution as reconstructing the dinosaur. Later stories can become more definite than surviving documents allow. The roadside discovery may have occurred as tradition describes, or the first teeth may have reached the Mantels through a more complicated network. A responsible account preserves Marianne's recognized association without claiming certainty where archives remain ambiguous. Iguanodon changed science partly by exposing these structures, how names gain authority, how institutions control specimens, how public images solidify hypotheses, and how corrections distribute credit. Its history is not only about replacing a horn with a thumb spike, it is about learning that every reconstruction, anatomical or historical, rests on selected evidence. Once the genus was narrowed, the animal did not become less interesting, it became more itself. The next question was no longer how many fossils could be called Iguanodon, but how much could be learned from the fossils that truly belonged there. Modern study often begins without touching the original fossil. A skeleton can be scanned with structured light, photogrammetry, or computed tomography. Surface models capture shape at fractions of a millimeter. Internal imaging reveals cracks, supports, restoration materials, and cavities hidden beneath bone. Digital copies can be rotated, measured, mirrored, and shared with researchers who may never travel to Brussels. This matters because the Bernissart specimens are fragile and historically mounted. Removing a bone from its support can create greater risk than the scientific question justifies. Digital models allow virtual disassembly. A distorted left bone can be compared with a better preserved right counterpart. Missing surfaces can be estimated. Joint positions can be tested without forcing the original skeleton into a new pose. The reconstruction becomes adjustable again. Three-dimensional models also support volumetric estimates of body mass. Researchers build a skeletal framework, add plausible muscle and soft tissue volumes, and calculate the density of the resulting body. Different assumptions produce a range rather than one perfect number. Limb bone scaling offers another method, comparing the dimensions of weight-bearing bones with those of living animals. When independent approaches overlap, confidence increases. Mass estimates for Iguanodon vary because individuals differ and because no fossil preserves the complete body outline. A deep gut, thick tail muscles, and substantial shoulder tissue add weight. Air spaces and lighter regions reduce it. A model that looks visually convincing may still distribute volume incorrectly. Paleontologists therefore test multiple reconstructions, not simply the most attractive one. The same digital body can be used to explore balance, Place the estimated center of mass above the hips and calculate how far it shifts when the neck lowers or the forelimbs contact the ground. Test joint ranges. Add the pull of major muscles. Compare the result with trackways. A posture that appears natural in an illustration may fail mechanically when weight and articulation are included. Finite element analysis can examine individual bones. The thumb spike, for example, can be modeled under forces applied from different directions. Stress patterns show where the structure is likely to resist loading and where it may fail. Such work cannot reveal intention, but it can test function. If a proposed behavior would consistently fracture the bone under modest force, that behavior becomes less plausible. If the spike tolerates substantial loading, defensive or social use remains mechanically possible. Mechanical competence does not prove habitual behavior. A human hand can withstand forces encountered in climbing, striking, and tool use, but bone strength alone cannot tell which action occurred. In Iguanodon, the thumb spike may have served more than one function. Evolution often retains structures that are useful across several contexts. The best interpretation combines mechanics with wear, injury, comparison, and ecological need. Bone histology opens another scale. A thin section cut from a limb bone can reveal vascular canals, growth lines, and changes in tissue organization. Fast-growing bone differs from slowly deposited bone. Periodic interruptions may reflect seasonal stress or normal growth cycles. Remodeling shows how old tissue was replaced as the skeleton carried increasing loads. From these patterns, researchers estimate age and growth trajectory. Sampling is destructive. A slice removed for histology cannot be returned. On a famous specimen, the decision carries scientific and ethical weight. Is the question important enough? Can an already broken surface be used? Does another specimen provide the same information? Modern collections balance preservation against the fact that a fossil protected from every analysis may preserve its material while withholding its evidence. Geochemistry extends the record into water, temperature, and movement. Oxygen isotopes can vary with climate and the source of drinking water. Strontium isotopes reflect geology in the landscape. Trace elements reveal diagenetic alteration. In the Bernissart collection, recent analyses have supported a picture of limited migration and seasonal conditions, while also documenting the chemical overprint created during fossilization. Pollen and spores provide an environmental counterpart. Sediment associated with Iguanodon remains can be processed to recover microscopic plant structures. These identify broad groups even where leaves and wood are absent. The resulting assemblage shows which plants grew nearby, which were transported by water or wind, and how vegetation changed through layers. Diet is inferred by combining those plants with feeding height and dental function. A fossil site becomes a network of datasets. Skeletons show bodies. Sediment shows deposition. Pollen shows vegetation. Isotopies show chemistry. Trackways show movement. Teeth show wear. Historical records show excavation context. No single line resolves the animal. Agreement across lines is more powerful than detail from one spectacular specimen. This is a major shift from the age of Mantell. Comparative anatomy remains central, but the scale of comparison has expanded. Mantell placed a fossil tooth beside an iguana tooth. A modern project may place a digital skull beside hundreds of specimens, model stress through the jaw, examine microscopic wear, sample isotopes, and test the animal's position in a phylogenetic matrix. The starting object can still be one tooth. The surrounding system has become far larger. Technology does not eliminate interpretation. Scans must be segmented. Missing tissue must be reconstructed. Character states must be coded. Statistical models require assumptions. A computer can calculate exactly from uncertain inputs. The apparent precision of a digital result can therefore be misleading if the biological uncertainty is hidden. Iguanodon's history warns against confusing detailed output with final truth. Recent locomotor research demonstrates this clearly. For decades, many reconstructions treated Iguanodon as comfortably switching between 2 and 4 legs. New quantitative approaches compare anatomical correlates across living and extinct animals and may support more constant quadrupedality in adults. The result is not accepted merely because it is new. It must be examined, replicated, and integrated with trackways, growth, joint anatomy, and prior work. The animal may change again. Future discoveries could include a juvenile growth series, skin impressions, better trackways, new European skeletons, or preserved stomach contents from a close relative. A new analytical method may reveal muscle arrangement or inner ear function with greater confidence. The history of Iguanodon gives no reason to expect the present reconstruction to be permanent. Permanence is not the goal. A scientific reconstruction succeeds when it explains available evidence better than the alternatives and states where it remains uncertain. The best modern Iguanodon is not the final animal. It is the most testable one. Museums increasingly communicate this by showing multiple reconstructions or explaining why historic mounts differ from current art. The contrast can be more educational than replacing every old display. Visitors see not only what scientists think, but how they came to think it. A nose horn beside a thumb spike becomes a lesson in anatomical context. A tail-dragging mount beside a horizontal model becomes a lesson in biomechanics. Digital access also changes who can study the fossils. High-resolution models can reach classrooms, artists, engineers, and researchers far from the collection. Students can measure a hand once restricted behind glass. Artists can reconstruct muscle on an accurate skeleton. Independent teams can test published claims. The specimen remains in Brussels while its geometry travels. This circulation echoes the older spread of drawings and casts, but with greater fidelity. 19th century engravings, sometimes simplified or misoriented bones. Plaster casts reproduced form, but required physical shipping. Digital models preserve surface detail and can be duplicated without wearing the original. They also create new responsibilities for metadata, scale, version control, and long-term storage. The tooth that began the story could fit in a small cabinet. The modern dataset built around Iguanodon can occupy servers, laboratories, and museum archives across countries. Yet the purpose remains recognizable: to infer the living animal from what survived. The tools have changed because the questions became more precise. Iguanodon changed science first by expanding the ancient world. It continues to change science by showing how that world must be rebuilt, collectively, quantitatively, and with enough humility to let a famous animal become unfamiliar again. Long before Iguanodon appeared, small bipedal ornithopods had already developed efficient ways to crop plants and escape predators. Their bodies were light, their hind limbs long, and their teeth arranged for repeated replacement. Across the Jurassic and early Cretaceous, some lineages grew larger, strengthened the forelimbs, widened the beak, and increased the complexity of the chewing apparatus. Iguanodon inherited this history. Its body was not an isolated invention, but one successful outcome of millions of years of ornithopod evolution. Ornithopods belonged to Ornithischia, the major dinosaur branch traditionally characterized by a backward-pointing pubis and a set of related skeletal features. The name means bird-hipped, though birds evolved from the other great dinosaur branch, the Saurischians. Historical labels can outlive the assumptions that made them seem intuitive. Iguanodon helped define early ideas about Ornithischian anatomy even before the larger evolutionary pattern was understood. Its beak was part of a broader herbivorous solution. Teeth at the front of a jaw are vulnerable when repeatedly cutting stems. A keratinous beak provides a renewable edge. Teeth farther back can specialize in processing. This division of labor appeared in several dinosaur groups, including ceratopsians and hadrosaurs, but each built the system differently. Iguanodon's beak was broad enough to gather substantial mouthfuls without becoming the wide duck-like bill of later hadrosaurids. The cheek teeth were arranged in vertical rows, with replacement teeth waiting beneath. Usually one functional surface dominated at a time, less densely packed than the multiple stacked teeth in advanced hadrosaur dental batteries. Wear produced sloping facets. The system was effective enough to handle tough vegetation while remaining anatomically simpler than what evolved later. It shows evolution working through accumulation rather than sudden perfection. Calling Iguanodon transitional can be useful, but the word can imply that the animal existed only to become something else. It did not. Its anatomy persisted because it worked in early Cretaceous environments. Later hadrosaurs inherited and modified some features, while other iguanodontian branches followed separate paths or disappeared. Evolution has no obligation to preserve every successful design indefinitely. The lineage that followed would produce some of the most abundant large herbivores of the late Cretaceous. Hadrosaurs occupied North America, Asia, Europe, and other regions. Their jaws carried hundreds of teeth organized into grinding batteries. Some developed elaborate crests used in display and sound production. Their trackways and bone beds show large populations. The feeding and locomotor foundation visible in Iguanodon helped make that radiation possible, even if Iguanodon itself was not a direct ancestor of every later form. This evolutionary position changed scientific interpretation in another way. The first Iguanodon tooth suggested a giant lizard-like herbivore. Later comparative work placed the animal within a dinosaur family tree, extending backward to smaller ornithopods and forward toward hadrosaurs. The tooth stopped being evidence for a strange, isolated reptile and became one expression of a long evolutionary experiment in plant eating. Size was part of that experiment. Growing larger reduces vulnerability to many predators and allows a digestive system to retain food longer, increasing the effectiveness of fermentation. Large bodies can travel efficiently across distance and tolerate short-term fluctuations in food. They also require enormous total intake and reproduce more slowly. Iguanodon's size represented a balance between these advantages and costs in productive but seasonally changing landscapes. The strengthened hand shows how increased size can reshape locomotion. A small ancestor can remain bipedal with light forelimbs. As the torso and gut enlarge, the center of mass moves forward. Supporting the body on four limbs becomes more useful. The central fingers thicken and align for weight-bearing. The wrist loses mobility in exchange for stability. At the same time, the outer digits retain specialized functions. Iguanodon's hand records the negotiation between support and manipulation. The thumb spike is especially revealing because it could evolve only within that altered hand. The first digit no longer needed to share ordinary grasping or weight-bearing duties with the others. It became free to specialize. The fifth digit moved in a different direction, retaining flexibility. Evolution did not redesign the limb from nothing. It modified each component according to the pressures acting on the whole animal. Whether the spike evolved mainly for defense, display, competition, or a combination remains uncertain. Similar uncertainty surrounds many striking structures in dinosaurs. Horns, crests, plates, and claws can perform several roles. Mechanical form narrows possibilities, but social behavior is rarely fossilized. Exaggerated structures often attract single-purpose explanations because they are visually memorable. Biology is usually less tidy. Iguanodon's predators were evolving too. Theropods changed in size, skull shape, forelimb anatomy, and hunting strategy across the early Cretaceous. Herbivore defenses therefore existed within an evolutionary relationship. Greater size, group awareness, locomotor performance, and weapons could reduce risk, while predators adapted to different prey. Neither side reached a permanent solution. Ecosystems remained dynamic because every advantage altered the conditions faced by other species. A healed fracture would show survival. A bite mark would show contact. A worn tooth would show feeding. Most behaviors leave no trace. Evolutionary anatomy fills the gaps cautiously by asking what a structure could do, what it was likely to do, and what consequences would follow. Iguanodon's history is a record of those three questions being confused and then separated. Early workers saw a conical bone and asked what it resembled. A horn seemed plausible. Bernissart showed where the bone attached. Modern mechanics asks how it responded to force. Each stage moves from analogy toward context. The same progression applies to the entire animal. A lizard provided the first comparison. Complete skeletons supplied relationships. Biomechanics and trackways test movement. Ecology and geochemistry test where that movement occurred. This expanding context is one of paleontology's greatest achievements. Extinct animals cannot be observed directly, but they can be constrained from many directions. The process rarely produces absolute certainty. It produces a narrowing field of plausible lives. Iguanodon changed science because it forced that field to narrow repeatedly in public view. Its role in the definition of Dinosauria also ensured that later discoveries were compared against it. When researchers debated whether dinosaurs were sprawling or upright, cold or active, solitary or social, Iguanodon supplied evidence. When museums needed a representative herbivore, it stood beside carnivorous dinosaurs. When textbooks illustrated scientific revision, its changing posture became a standard sequence. There is a risk in allowing one animal to carry too much. Iguanodon was not typical of every dinosaur. Its hand was unusually specialized. Its feeding system belonged to one branch. Its size and posture do not describe sauropods, armored dinosaurs, or theropods. The category Dinosauria grew far beyond the three genera Owen first used. Modern birds alone show how diverse the group became. Yet representative animals matter because science is learned through examples. Iguanodon made herbivorous dinosaurs imaginable. Bernissart made complete dinosaur skeletons believable. The historic mounts made posture visible. Taxonomic revisions made the instability of names understandable. Few genera connect so many stages of the discipline. The connection reaches into living landscapes. Birds are dinosaurs, but they are not descendants of Iguanodon. They come from small theropods on the other side of the dinosaur family tree. Still, every bird demonstrates that dinosaurs were not an evolutionary failure waiting for extinction. Iguanodon and its world belonged to a radiation whose surviving branch remains active around us. The non-avian ornithopods ended at the close of the Cretaceous, but their ecological roles did not vanish permanently. Mammalian herbivores later evolved beaks in some lineages, complex grinding teeth in others, large fermenting guts, herd behavior, and weight-bearing limbs. These are not direct inheritances from Iguanodon. They are recurring solutions to the physical problem of living on plants. Iguanodon shows one of those solutions at a scale the modern world no longer contains. A several-ton dinosaur with a cropping beak, renewable tooth rows, a massive gut, hoof-like fingers, a mobile fifth digit, and a thumb transformed into a spike. Its strangeness does not come from being primitive. It comes from being highly adapted in a way no living animal repeats. To see it clearly, science had to stop forcing it into the shapes of living animals. The giant iguana, the reptilian rhinoceros, and the kangaroo all supplied temporary support. The mature reconstruction emerged when Iguanodon was allowed to have its own body. The scientific life of Iguanodon has always unfolded in public. Its teeth appeared in books intended for educated readers beyond specialist circles. Its body became a sculpture in a pleasure park. Its skeletons became national exhibits in Brussels. Each form reached people who would never handle a fossil or read an anatomical monograph. The dinosaur grew alongside the institutions through which modern science learned to present itself. Natural history museums in the 19th century were reorganizing private collections into public evidence. Objects once kept in cabinets of curiosity were labeled, classified, and placed within narratives of geological time. Large fossils were especially valuable because they made the scale of the past visible. Iguanodon offered both spectacle and instruction. Its skeleton could attract a crowd while its teeth, limbs, and posture introduced comparative anatomy. The Bernissart discovery also became important to Belgian national identity. The skeletons were found only decades after Belgium became an independent country. Their excavation required state institutions, mining expertise, and museum labor. Displaying them in Brussels demonstrated scientific capacity as well as prehistoric life. Fossils can become national symbols even though the animals lived before modern borders existed. This creates tension. A fossil belongs legally to a collection or country, but scientifically it belongs within a global history of life. Iguanodon moved through British and Belgian narratives, yet the early Cretaceous landscape ignored those boundaries. Populations occupied changing islands and lowlands across Western Europe. Their fossils were separated later by geology, erosion, ownership, and museum practice. Casts helped bridge that separation. A mold taken from an original bone could produce copies for other institutions. Entire skeletons could be replicated and mounted in different poses. Casts expanded access without dividing the original specimen. They also spread particular reconstructions rapidly. An error in the source mount could travel as efficiently as a correct detail. Illustrations traveled even farther. Engravings of the Crystal Palace models entered newspapers and books. Drawings of the Bernissart skeletons established the upright animal internationally. Later paintings placed Iguanodon in forests, often fighting predators or standing in groups. Each medium selected a different aspect: scale, anatomy, action, or atmosphere. The animal people knew depended on the image they encountered first. Popular culture can preserve outdated reconstructions long after specialists revise them. This is not only because artists resist correction. Familiar silhouettes are easier to recognize. An upright iguanodon with raised arms looks distinct from a more horizontal animal that resembles other large ornithopods. The nose horn, though wrong, gives the Crystal Palace model a strong identity. Scientific accuracy and visual memory do not change at the same speed. Historic errors can still carry value when they are understood. The Crystal Palace sculptures are not failed models waiting to be discarded. They are surviving records of what evidence meant in the 1850s. The Bernissart mounts are not useless because their tails bend incorrectly. They preserve one of the most influential stages in dinosaur reconstruction. Their age allows us to see science moving. Removing every outdated image would create a false impression that knowledge arrived complete. A museum that explains revision can be more honest than one that shows only the current answer. Iguanodon is uniquely suited to this layered display because its transformations are so physical. Visitors can move from horn to thumb, from forelegs to tripod, from tripod to horizontal body, and from broad genus to narrow taxon. The story also reveals how scientific authority is built. Owen's interpretation gained reach through institutions and public projects. Mantell's contributions survived through publications and collections, but were affected by health, finances, and rivalry. Dallow's reconstruction gained authority from the completeness of Bernissart. Modern teams gain authority through reproducible methods, open data sets, and peer review. Evidence matters at every stage, but the channels carrying evidence change. It would be misleading to portray these figures as simple heroes and villains. Mantell made mistakes and sometimes overextended interpretations. Owen made lasting anatomical contributions even while his treatment of rivals attracted criticism. Dallow corrected earlier models and created a new error. The history is useful precisely because insight and limitation coexist in the same people. The miners deserve a place within it. They recognized unusual material in dangerous conditions, protected it long enough for specialists to respond, and performed much of the physical work of excavation. Preparators turned fragile blocks into accessible bones. Conservators kept those bones from breaking apart. Illustrators recorded them. Museum staff maintained displays. The famous name on a publication represents a much larger human chain. Paleontology depends on this chain today. Field crews include geologists, preparators, students, local workers, land managers, and specialists. Laboratory analysis may involve engineers, chemists, statisticians, and computer scientists. Iguanodon's modern reconstruction is collective in a way no single portrait can show. The discipline changed from gentlemen naturalists with private cabinets into collaborative teams working across institutions. Public participation remains important. Fossils are often found by quarry workers, coastal collectors, farmers, hikers, or construction crews. Recognition can determine whether a specimen reaches science or disappears. The first Iguanodon teeth came from a landscape where ordinary work exposed ancient rock. Bernissart repeated the pattern underground. Discovery often occurs where deep time intersects with daily labor. The animal also changed the language available to the public. Before Dinosauria, there was no familiar category for a giant herbivorous reptile from the land. After Iguanodon and its companions, dinosaurs became a recognizable kind of ancient life. Over time, the category expanded from a few massive reptiles to include tiny feathered forms, social nesting colonies, polar species, and birds. The word remained while its contents transformed. Iguanodon can therefore be seen as both a dinosaur and a machine for producing dinosaur images. Its fossils generated comparisons, models, exhibits, and arguments. Each image influenced the next generation of questions. The Crystal Palace body made size public. Bernissart made skeletons public. Modern digital models make uncertainty and alternative poses public. The animal's scientific impact lies partly in this repeated translation. Translation always loses something. A full skeleton omits skin, color, behavior, and sound. A life reconstruction hides which parts are known. A documentary compresses decades of debate into minutes. A museum label reduces a species to a few sentences. Responsible communication does not eliminate compression, it signals where compression occurs. This is why the changing Iguanodon remains more useful than a single perfected picture. It teaches that a reconstruction has a date. The animal lived once, but humans have rebuilt it many times. When the rebuild changes, the fossil has not betrayed science. Science has learned to ask the fossil a better question. 200 years after the first description, Iguanodon still stands near the foundations of dinosaur research. It is present in the origin of Dinosauria, the first monumental prehistoric park, the first great assemblage of complete dinosaur skeletons, the development of museum mounting, the rise of biomechanical reconstruction, and the modern revision of dinosaur taxonomy. Few animals have occupied so many turning points. Its public history prepares us for the deeper scientific lesson. Iguanodon did not change science by offering one perfect answer. It changed science by refusing to remain the animal people expected. What then? Did Iguanodon actually change? The first change was ecological. Its teeth established that gigantic prehistoric reptiles could be herbivores. That conclusion seems ordinary now because dinosaur books are filled with sauropods, horned dinosaurs, armored dinosaurs, and hadrosaurs. In 1825, it expanded the known structure of ancient terrestrial life. Large reptiles were not only hunters. They occupied different levels of a food web, and the world that supported them required vegetation on a corresponding scale. The second change was classificatory. Iguanodon joined Megalosaurus and Hylaeosaurus in Owen's Dinosauria. The new group separated these animals from ordinary lizards and recognized a distinctive terrestrial anatomy. The definition was revised many times, but the act of grouping changed the direction of research. Fossils could be compared within a shared evolutionary and anatomical framework. Dinosaurs became a subject rather than a series of unrelated curiosities. The third change was visual. Crystal Palace gave prehistoric animals full-sized public bodies. Iguanodon stood at the center of the experiment. The model was inaccurate, but it demonstrated that fossil science could reconstruct an environment large enough to enter. Modern dinosaur parks, museum dioramas, cinema, and digital worlds inherit that decision to turn fragmentary evidence into spatial experience. The fourth change came from Bernissart. Complete skeletons replaced speculation with context. The thumb spike moved to the hand, limb proportions became measurable. Multiple individuals revealed variation. The site proved that dinosaur discoveries could occur on the scale of a population and that industrial excavation could recover extraordinary paleontological archives. It also created new standards for mounting, preparation, and conservation. The fifth change was methodological. Iguanodon's repeated reconstruction showed that complete bones do not guarantee correct posture. Functional anatomy, trackways, joint limits, balance, and soft tissue inference had to be integrated. The upright tripod gave way to a horizontal body. The forelimb returned to the ground. More recent studies continue to test how fully quadrupedal the animal was. Reconstruction became an explicit, mechanical hypothesis. The sixth change was taxonomic. The collapse of the old wastebasket genus demonstrated the need to distinguish similarity from identity. Fossils once gathered under Iguanodon were distributed among many genera. The type species was stabilized. Population-level variation at Bernissart helped test diagnostic features. The process made dinosaur classification more rigorous and revealed diversity that a famous name had concealed. The seventh change is still occurring through modern analysis. Isotopies investigate movement and seasonality. Paleontology connects jaws to plants. Histology studies growth. Digital models test mass and posture. Finite element analysis examines the thumb spike. Conservation science maps pyrite decay. Iguanodon has become a platform on which new methods encounter old specimens. These changes do not form a straight ascent from ignorance to truth. Some happen together. Some reversed earlier ideas and later required revision themselves. The Crystal Palace model was both wrong anatomy and successful communication. Dallow's mount was both a major correction and a biomechanical error. The narrowing of the genus removed old species while strengthening the identity of the remaining one. Progress arrived through mixed outcomes. That is what the skeleton under glass can show better than a polished final image. Science is not a sequence in which falsehood disappears and certainty accumulates without cost. It is a practice of making models answerable to evidence. A model can be useful before it is complete. It can remain culturally important after it is anatomically obsolete. It can be corrected without erasing the work that made correction possible. Iguanodon is almost uniquely suited to carry this lesson because each stage became monumental. The first tooth entered the literature. The first body became architecture. The Belgian skeletons became a cathedral of bone. The modern animal became a digital structure that can be rebuilt on a screen. The scale of representation grew with the scale of the questions. Consider the thumb spike through that entire history. It began as an isolated conical bone. It became a nasal horn. It was sculpted above the snout at Crystal Palace. Bernissart placed it on the hand. Artists turned it into a dagger. Engineers later tested how it handled force. Researchers now discuss defense, display, competition, and multifunctionality. One bone records the movement from resemblance to anatomy to biomechanics. The tooth offers a parallel path. It began as an iguana comparison. It established herbivory and gave the genus its name. Complete jaws revealed replacement patterns and wear. Microscopic and comparative studies placed it within the evolution of ornithopod feeding. Pollen and spores helped identify likely plant communities. The smallest original evidence remained scientifically productive after the largest skeletons were found. This continuity matters because new evidence does not always replace old evidence. Sometimes it changes the questions old evidence can answer. Mantell's tooth is no longer asked to provide the whole body. It can instead reveal the history of naming, the logic of early comparative anatomy, and the details of dental function. The Crystal Palace model no longer describes the living dinosaur, but it precisely describes a moment in scientific culture. Bernissart's upright mounts operate in the same way. Their posture is outdated, yet their bones remain original, and their arrangement preserves the history of 19th century reconstruction. Correcting the science does not require pretending the mount never existed. It requires labeling the difference between specimen and pose. Paleontology always works across this difference. The fossil is material evidence. The mount is an interpretation. A published species name is an interpretation. A phylogenetic tree is an interpretation. A climate estimate is an interpretation. These interpretations can be tested because they make claims about material patterns. Iguanodon became famous partly because the separation was repeatedly exposed. Public trust in science can suffer when revisions are presented as contradiction without process. The changing Iguanodon offers a better explanation. Earlier researchers made the strongest animal they could from limited remains and available analogs. New skeletons revealed errors. Later biomechanics revealed errors in the new skeleton mounts. Current work examines assumptions in the modern model. Revision is not evidence that nothing is known. It is evidence that claims remain accountable. We know far more than the first investigators did. We know Iguanodon was a large early Cretaceous ornithopod, a herbivore with a beak, replacement teeth, powerful hind limbs, weight-bearing hands, a stiffened tail, and specialized digits. We know the Bernissart animals lived in a seasonal freshwater landscape and were buried within an unusual geological basin. We know the old nosehorn and kangaroo posture were wrong. Uncertainty survives around behavior, exact locomotor habits, death scenarios, and some relationships. The known and unknown are not equal. Uncertainty does not return the animal to a blank space. It occupies defined margins around a strong anatomical core. We may debate how often an adult used 2 legs, but not whether the thumb spike belonged on the nose. We may debate why many individuals accumulated at Bernissart, but not whether the deposit contained multiple articulated skeletons. The field becomes more precise by locating disagreement. This precision is Iguanodon's final scientific contribution. It taught paleontology to become comfortable with an animal that is neither fixed nor unknowable. The past can be reconstructed without being fully recovered. Evidence can support confidence without demanding certainty. A picture can be useful while carrying a date. Somewhere in southern England, more Wealden rock is eroding. On the Isle of Wight, cliffs release bones after storms. In Spain and elsewhere in Western Europe, new Iguanodontian remains continue to refine the group. A future specimen may change the genus again. It may preserve a hand in a new orientation, a juvenile skull, a skin impression, or a set of bones associated with plant material. Iguanodon's history makes every apparently settled feature worth testing. The animal that changed science did not do so by remaining stable. It changed science because every time humans thought they had completed it, the stone offered another correction. Return to the floodplain before the mine, the museum, and the name. Morning light reaches across shallow water. Mist hangs low over a channel abandoned by the river. Ferns spread from damp ground in dense green patches. Conifers stand on slightly higher soil, their roots holding banks built from older floods. Somewhere beyond the trees, a large animal moves through vegetation, heard first as branches shift and stems break. An adult Iguanodon enters the open ground. Its body is held forward, the tail extended behind, the torso broad, with the machinery of digestion. The head is smaller than the body suggests it should be. The beak closes around a cluster of leaves. Farther back in the mouth, teeth meet and wear against one another. The animal steps, pauses, and feeds again. Nothing in the movement resembles the rigid forms that will one day stand in parks and galleries. Its weight passes through the hind feet and, when the forelimbs contact the ground, through the central fingers of the hands. The palms face inward. The thumb spikes remain clear of the soil. The fifth digits curve away from the supporting column. Each part of the hand performs within a structure that took generations of scientists to understand. Here, it operates without explanation. Other iguanodons may be nearby. Perhaps they are a stable group, perhaps a temporary gathering along water, perhaps individuals using the same feeding ground. The fossil record cannot choose confidently among those possibilities. The landscape can support all of them. Tracks cross older tracks. Some fill with water, others dry and crack before another flood covers them with silt. A juvenile would differ from the adult in more than size. Its limbs would carry different proportions, its center of mass would shift as it grew, and its behavior might depend more strongly on cover or companions. Young bone would deposit rapidly. Teeth would replace in a smaller jaw. The dangers around it would be different. A predator unable to threaten the adult could still take the juvenile. Along the channel, a crocodilian lies almost submerged. Fish move beneath the surface. A theropod has passed through the area earlier, leaving narrow three-toed prints in firmer mud. The iguanodon does not need to fight. Most successful defense consists of noticing danger before contact, keeping distance, and moving with enough power that pursuit becomes costly. The thumb spike is present without being used. The day warms. Moisture rises from the ground. Insects move through fern beds and around fallen wood. Pterosaurs cross above the canopy, distant enough to appear briefly between branches. There are no grasses underfoot and no modern broadleaf trees overhead. Early flowering plants exist in the wider world, but the familiar angiosperm landscape has not yet taken control. Conifers and ferns remain central to the food web. The animal browses across the edge of woodland, taking foliage from different heights. It does not chew like a cow, but it processes food in the mouth before swallowing. The beak crops. Teeth shear and grind along worn surfaces. The tongue positions the plant matter. The gut will continue the work for hours or days through fermentation. This repeated act, more than any encounter with a predator, defines the life of a large herbivore. Every few weeks or months, another tooth moves toward function as an older one wears away. Bone remodels under load. Muscles strengthen around joints. Seasonal chemistry enters growing tissues through water and plants. Without intention, the animal creates a record. Most of it will vanish. A fraction may survive in enamel, mineral, and microscopic structure. The body before us is complete, warm, and self-repairing. The fossil will be none of those things. Death will remove muscle and skin. Scavengers and microbes will separate systems that work together. Burial will flatten the three-dimensional animal. Mineral water will change its chemistry. Excavation will divide it into blocks. Preparation will rebuild continuity. Every future image will begin from loss. Perhaps this individual never enters the Bernissart Basin. Most iguanodons did not. It may die on an exposed floodplain where bones scatter and weather away. A tooth may travel down a river. A femur may settle in sand. A footprint may survive after the maker has moved far beyond it. The fossil record is not a census of the living population. It is the small remainder selected by circumstance. That selection shaped the history of science. Southern England offered teeth and fragments, so the first iguanodon was built from comparison. Bernissart offered articulated skeletons, so the second was built from anatomy. Museums offered fixed mounts, so posture became a public certainty. Digital tools offered adjustable models, so the animal could become provisional again. Evidence did not simply increase. Its form changed. The roadside tooth and the Belgian skeleton answer different questions. The tooth reveals feeding and the moment of recognition. The skeleton reveals body plan. The bone bed reveals population variation and burial. The historic mount reveals interpretation. The conserved specimen reveals chemistry. No single object contains the entire iguanodon. The animal emerges from relations among them. This is true of every dinosaur, but Iguanodon makes the process unusually visible. Tyrannosaurus entered science when paleontology already possessed the category dinosaur. Iguanodon helped create the category. Later, dinosaurs were mounted after generations of anatomical experience. Iguanodon helped establish the practice of mounting. Modern genera are named within a mature taxonomic system. Iguanodon survived the period when that system was being invented. Its age in science is now almost 2 centuries. In that time, continents have not moved far enough to notice without instruments, but the scientific animal has crossed enormous distances. It moved from reptile to dinosaur, from quadruped to biped and back toward quadrupedality, from worldwide genus to a narrower lineage, from public sculpture to digital mesh. The fossil record remained finite while interpretations multiplied. Some details may still reverse. A locomotor study can challenge the familiar facultative biped model. A new phylogenetic analysis can move Iberian species outside the genus. Geochemical work can restrict migration. Better sedimentology can replace a single catastrophic death with repeated events. Each result must survive scrutiny. The correct response to Iguanodon's history is not to distrust every reconstruction, but to ask how each one is supported. Evidence has weight. An articulated hand outweighs resemblance when locating the thumb spike. Ossified tendons outweigh a convenient museum pose when reconstructing the tail. Multiple skeletons outweigh one unusual bone when assessing variation. Stratigraphy outweighs a dramatic story when testing whether deaths were simultaneous. Science advances by deciding which evidence bears directly on which claim. The first discoverers could not perform those tests because much of the evidence had not yet been found. Their errors became visible only later. Our own errors may be equally dependent on evidence still underground. Somewhere a skeleton could preserve the feature needed to resolve posture, growth, or identity. Until then, uncertainty is not an empty phrase. It is a marked place where discovery can still enter. Museums protect those marked places by preserving specimens beyond the questions of the present. Mantell could not anticipate isotopic analysis. Dallo could not anticipate digital finite element models. Conservators now maintain bones for methods that do not yet exist. A fossil collection is therefore a scientific reserve. Its future value may depend on details no current researcher knows to examine. This is why the Bernissart iguanodons remain more than famous displays. Their large number permits questions about variation. Their historical excavation records permit taphonomic reconstruction. Their chemical instability drives conservation research. Their old mounts preserve scientific history. Their anatomy continues to test locomotion and function. The collection is not finished because the exhibition is complete. The original English material remains important for the opposite reason. It is incomplete. Those teeth show how a discipline begins when evidence is scarce. They preserve the risk and power of analogy. Mantell saw a similarity to an iguana and used it to infer diet. He also participated in reconstructions that placed the animal within familiar bodies. One comparison opened the door. Too much dependence on comparison narrowed the room beyond it. The mature science of Iguanodon learned to use living animals without forcing extinct ones to become copies. Iguanas still help explain tooth shape. Birds and crocodilians help constrain soft tissues and physiology. Large mammals help test mass and support. No analog is allowed to supply the whole creature. The dinosaur is reconstructed at the intersection of comparisons, not inside any one of them. In this sense, Iguanodon changed more than paleontology. It helped teach science how to imagine responsibly. Reconstruction is necessary when direct observation is impossible. Imagination fills missing skin, behavior, and environment. Evidence limits that imagination. The strongest image is not the most dramatic one. It is the image that can show where bone ends and inference begins. The animal on the floodplain lowers its head again. Mud presses around the toes. A forefoot settles lightly, leaving the central digits in the surface while the thumb spike remains above it. The body moves forward. The print holds for a few minutes in sharp detail, then water seeps into its edges. By evening, the outline is softer. If sediment covers the track quickly, it may enter the geological record. If not, rain will erase it. The same is true of the bitten branch, the dung, the sound, and the social distance between animals. Almost all behavior disappears. Paleontology works with the exceptional residues of ordinary life. Its grandest conclusions often rest on marks made without permanence in mind. Later, perhaps during a seasonal flood, the river rises beyond its channel. Water moves through the fern beds and carries branches across the plain. Sand fills low areas. Clay settles in quieter water. Animals move toward higher ground. Some escape. Some do not. The landscape records the event as a thin layer that will be compressed beneath many more. The Bernissart Basin may receive a carcass during one such episode, or through a slope failure, or after an animal dies near deep water. The precise sequence remains under investigation. The body settles where oxygen is limited and scavenging reduced. Fine sediment closes around the limbs. Pyrite begins forming in spaces once occupied by tissue. The process that preserves anatomy also plants the chemistry of future decay. Millions of years pass without witness. Sediment becomes rock. Continents continue moving. Seas enter and retreat. The last non-avian dinosaurs disappear. Mammals diversify. Ice sheets grow and melt. Rivers carve new routes. Human beings arrive in landscapes that contain no visible sign of the animal below. Then, tools cut into stone. A road exposes a tooth. A quarry opens a slab. A coal mine crosses a clay-filled pit. The dinosaur returns in pieces, not to life but to attention. Each discovery changes what the pieces are allowed to mean. The past does not speak. It constrains the stories told about it. Iguanodon's story is often summarized with 4 pictures: the horned quadruped, the upright tripod, the horizontal biped, and the modern animal on 4 limbs. The sequence is memorable, but the deeper history lies between the pictures. It lies in the arguments, preparation, measurement, chemical treatment, taxonomic decisions, and repeated willingness to take a famous skeleton apart conceptually. That willingness is the real transformation. Early paleontology needed confidence enough to name an animal from teeth. Later paleontology needed humility enough to narrow the name. Museum builders needed confidence enough to mount a skeleton. Later biomechanists needed humility enough to show that the mount could not stand that way. Iguanodon advanced science by requiring both qualities. The next reconstruction may look only slightly different. The shoulders may carry more muscle. The hands may bear weight more consistently. The tail may shift in angle. The lips, cheeks, and beak may be redrawn. Small changes can alter behavior and silhouette without producing another dramatic Victorian reversal. Greater precision often arrives quietly. A future visitor may stand before the Bernissart skeletons and see 3 animals at once: the early Cretaceous herbivore, the 19th century upright reconstruction, and the modern model described on the label. None cancels the others. One is biological history. One is scientific history. One is the current attempt to connect them. Above that visitor rises an animal discovered before anyone fully understood what a dinosaur was. Its teeth helped reveal a herbivore. Its bones helped define Dinosauria. Its sculpture helped create public prehistory. Its skeletons corrected the sculpture. Its anatomy corrected the skeleton mount. Its variation corrected the genus. Its chemistry now corrects assumptions about movement and burial. Few fossils have asked science to change directions so many times. At the beginning there was a tooth, small enough to hold between finger and thumb, worn by a mouth feeding in a Cretaceous landscape. The animal that carried it is gone. The forests are gone. The river has changed course beyond recognition. What remains is enamel, bone, stone, and the record of every careful correction made around them. Iguanodon changed science because it showed that the ancient world could be known, and then showed that knowing it would never mean finishing it. The tooth rests in its case. The thumb spike stands on the hand. Beneath the glass, the old skeleton keeps its impossible pose, while the animal itself continues to move beyond it.